Hello. Welcome back to Sleep Science. Wherever you are right now, whatever the room sounds like, whatever time it is, every atom in your body was created in the first 10 minutes of the universe. Tonight we go back there, to the very beginning, to the moment before anything existed, and we watch it begin. So settle in. Let whatever you were carrying today set itself down somewhere nearby. You do not need to hold it right now. The ceiling above you has been there long enough to wait a few more hours. The floor beneath you, whatever it is made of, wood or concrete or carpet or old stone, has been supporting weight since long before you arrived. And it will keep doing that while you sleep. There is nothing you need to do, only listen. We are going back 13.8 billion years tonight, and I want you to know before we start that this is not a frightening story. It is not a violent story, though the temperatures involved are beyond anything the word violent was designed to describe. It is, actually, one of the quietest stories I know, because at the end of it, at the very end, after all the physics and all the fire and all the extraordinary machinery of the early universe, what you get is this: a room, a person, a body lying still, atoms that have been traveling 13.8 billion years, arriving here at rest for a few hours tonight. That is where this story ends. But first we go back to where it begins. And where it begins is nothing, or something so close to nothing that the difference may not matter. We will spend some time there, in the nothing or near it, sitting with the strange fact that there was a moment, if moment is even the right word, and we will get to why it might not be, when none of this existed. Not just when this room did not exist, not just when the earth did not exist, when space did not exist, when time itself in any meaningful sense did not exist, when the four fundamental forces that govern everything that happens in this universe had not yet separated into four different things, when the laws of physics as we know them had not yet settled into their current shapes, when there was, as near as we can say, nothing. And then there was something. That transition from nothing to something, from the absence of everything to the beginning of everything, happened so fast that the word fast is not even really applicable. It happened in a span of time that makes the blink of an eye look like a geological era. It happened, and from that happening, everything followed. You followed. This room followed. Every star you have ever seen in the night sky, every ocean, every stone, every living thing that has ever drawn a breath, every thought that has ever occurred in any mind, anywhere in the history of this planet, all of it followed from those first extraordinary moments. We are going to walk through those moments tonight, step by step, second by second, sometimes fraction of a second by fraction of a second. Because the first 10 minutes of the universe were, in terms of raw change per unit of time, the busiest 10 minutes in the history of everything. More happened in the first second of the universe's existence than happened in the following 5 billion years, and we are going to sit with that. We are going to let it be real. But gently. There is no hurry here. The universe is not going anywhere. You are not going anywhere. We have all night. So close your eyes if you have not already. Let your breathing find its own pace, whatever pace it wants, without adjustment or correction. Notice the weight of your body against whatever surface is supporting you. The slight press of the bed or the floor or the chair against your back, your legs, your head, the temperature of the air, the relative quiet of the room. Those atoms in your hands right now, the hydrogen in the water in your cells. Some of those hydrogen atoms are genuinely, specifically ancient, forged in the first 10 minutes of the universe itself, not in a star, not in any secondary process. In the direct, immediate aftermath of the Big Bang, when the universe was a matter of minutes old and still cooling from temperatures beyond imagination. The carbon in your bones and the oxygen in your blood were made later, in the cores of stars that lived and died billions of years before the Earth formed. The iron in your hemoglobin, carrying oxygen through your bloodstream right now as you listen, that came from supernovae. Stars so massive they could only end by exploding, and in those explosions they seeded the galaxy with the heavy elements that simpler stars could never make. But the hydrogen, the lightest element, the simplest atom, one proton and one electron, some of that hydrogen has been hydrogen since the first 10 minutes. It did not pass through a star. It did not need to. It was made directly from the conditions of the early universe, from the heat and the density and the brief window of time when the physics of nucleosynthesis was possible. And now it is in you. It is part of your cells. It is traveling with you wherever you go. This ancient hydrogen, this relic of the first minutes of everything, embedded in your biology as casually as if it were nothing at all, which is something to think about as you settle in. You are not an observer of the cosmos looking outward at a history that happened elsewhere. You are made of that history. The earliest moments of the universe are not something you read about at a remove. They are constitutive of you. The beginning of everything is inside you right now, tonight, in the chemistry of your embryonic cells. And tonight, we go back to find it. We start from the very beginning, from before beginning, from the moment where the word moment itself loses its usual meaning, and we walk forward step by step through the first 10 minutes until we arrive at a universe that is recognizably the precursor to the one we inhabit. This is a story about where you came from, not your family or your culture or your country or your century, where you really came from, where everything really came from, 13.8 billion years ago, in a place that was not yet a place, in a time that was not yet time. The room is quiet, your breathing is slow. The atoms in your body, hydrogen from the Big Bang, carbon from dead stars, iron from supernovae, are all at rest for a few hours. Let's begin. Take one slow breath, not deliberately slow. Just let it be whatever it is, and we start. There was, before the universe began, no space in which the universe could begin. There was no darkness waiting to be lit. There was no emptiness waiting to be filled. Those concepts, darkness, emptiness, waiting, all require space to be meaningful, and there was no space. There was no time before which the universe did not exist. There was no moment of anticipation before the first moment. Time, as best we understand it, is a feature of the universe, not a container it was poured into. There was just, and the word just is doing a lot of work here, the beginning, and from the beginning, everything, including at the far end of a 13.8 billion year chain of consequence. You, this room, this night, these few quiet hours. Let the weight of your body go. We are going back now. Think about the room you are in right now, the ceiling above you, the walls, the floor. They all look ordinary. They are ordinary in the sense that you have been surrounded by such things your entire life and have no special reason to find them remarkable. But they are not ordinary at all. The ceiling above you is made of atoms, carbon atoms, oxygen atoms, hydrogen atoms, silicon atoms, calcium atoms, iron atoms, an enormous number of atoms, trillions of trillions, beyond any count the imagination can hold. And those atoms, every single one of them, have a history that predates the Earth, a history that predates the Sun, a history that, in the case of the hydrogen atoms, predates every star that has ever existed. The calcium in the plaster of the ceiling, if the ceiling is plastered, was made in a star that lived before the Sun, a star that fused hydrogen into helium in its core for millions or billions of years, then fused helium into carbon and oxygen, then burned through its heavier elements, then exploded in a supernova that scattered its products into the galaxy. Some of that calcium, scattered by that explosion billions of years ago, eventually found its way into the cloud of gas that became the solar system, into the Earth, into limestone deposits, into the materials used to build the ceiling above you. The iron in any metal in this room, a nail, a bracket, a hinge, was made in a stellar core. the end product of the fusion chain that powers massive stars. The element whose formation signals the death of a star because iron cannot power further fusion. Made in a core that collapsed, sparked a supernova, scattered the iron outward and the hydrogen. If there is wood in this room, or fabric or any organic material, it contains hydrogen atoms bonded to carbon. And some of those hydrogen atoms, some significant fraction of them, were made in the first 10 minutes of the universe. In the Big Bang nucleosynthesis we are going to describe tonight, they were never inside a star. They have been hydrogen since the universe was 10 minutes old. There is primordial hydrogen in this room, in the wood, in the fabric, in the air, in the water, in any glass that might be nearby, in the biology of your own cells. It has been travelling for 13.8 billion years, and it is here, in the room where you are resting. Let that settle in as we begin. Not as an abstraction, as a physical fact about the specific matter in your specific room tonight. You are surrounded by the ancient universe. The beginning is in the walls, in the ceiling, in the floor, in the air, in you. And we are going back to find it. So I want you to really settle in for a moment before we go anywhere. Feel the bed or the floor or the surface you are lying on, not as a mental exercise. Actually feel it. The slight give, the temperature, the way it holds you, your spine, your hips, your shoulders, your head, each part of your body supported. The earth beneath the floor, beneath you, 6,000 kilometers of rock and iron and silicate down to the core. The planet itself, a ball of matter orbiting a star 150 million kilometers away. The star, our sun, orbiting the center of the Milky Way galaxy once every 225 million years, currently somewhere in one of the galaxy's spiral arms, unremarkable among the 400 billion stars in the galaxy. The galaxy itself, one of perhaps 2 trillion galaxies in the observable universe. All of that context, all of that scale, and in the midst of all of it, you, a particular arrangement of matter lying still, breathing slowly on one surface of one planet, orbiting one star in one galaxy among trillions. You are not lost in this vastness. You are part of it. The atoms in your body are the same kind of atoms that make up the stars and the planets and the vast clouds of gas between them. The hydrogen in your cells is chemically identical to the hydrogen in the sun. The carbon in your DNA is chemically identical to the carbon drifting in interstellar molecular clouds. You are not separate from the cosmos. You are made of it, constitutively, in every atom. And that continuity, the fact that there is no fundamental break between you and the material world, that you are composed of the same stuff as everything else, that continuity extends backward in time as well as outward in space. The stuff you are made of has been around since near the beginning. Some of it has been around since the very beginning. And that is what we are going to trace tonight. The beginning. Not the beginning of human civilization, which is recent. Not the beginning of life on Earth, which is old, but not the oldest thing. Not even the beginning of the solar system, which is 4.6 billion years old. The actual cosmological everything. There is beginning 13.8 billion years ago, when the laws of physics and the 4 fundamental forces and the particles that make up matter were just finding their forms. When the universe was so hot that atoms were impossible. When it was so hot that even protons were impossible. When the matter that would eventually become you was part of a roiling, unimaginably energetic plasma of quarks and gluons. That is where we start. Not with you, not with the Earth, not with the Sun or the Milky Way, with the quark-gluon plasma of the first microsecond. And then we move forward, step by step, second by second, through the extraordinary first 10 minutes. At the end of the story, we arrive here, at this room, at you, at rest. The beginning and the end of the beginning and everything in between. That is the story of tonight. Take one more slow breath, and we go back. At 13.8 billion years ago, there was no space, there was no time. There was no darkness, because darkness requires space to exist in. There was nothing, and then in less time than it takes a single neuron in your brain to fire, everything began. Not with a bang, exactly, with something stranger than that. Something that physics can describe but the human mind cannot hold. Let's sit with that for a moment. The question of what existed before the Big Bang is one of the most honestly humbling questions in all of physics. And the honest answer, the answer that the best cosmologists and physicists alive today will give you if you press them, is that the question may not be meaningful. Not because we do not know the answer, but because the framework inside which the question makes sense may not apply to the situation. Before the Big Bang, the word before implies time. It implies a sequence of moments, one following another, a past that preceded a present. And time, as we experience it, as we measure it, as physics describes it, is part of the structure of the universe itself. Time, according to our best understanding, began with the universe. Not at some point shortly after the universe started, at the start. Time is not a container that the universe exists inside. It is more like a feature of the universe, something that emerged along with everything else, something that did not pre-exist the beginning and therefore cannot, strictly speaking, have a before. Which is strange when you think about it. More than strange. It is the kind of thing that if you allow yourself to really sit with it, produces a particular quality of quiet in the mind, because you reach for the concept of before and there is nothing there to grab. You reach back, meant past the first moment, and the reaching itself stops making sense. Like trying to walk north of the North Pole, the direction exists as a direction until you reach the pole. At the pole itself, it ceases to exist as a meaningful direction. There is no north of the North Pole, not because there is a wall there, but because north is defined relative to the poles. And at the pole itself, the definition breaks. There is no before the Big Bang for an analogous reason. Before is a temporal relationship. At the beginning of time, temporal relationships had not yet emerged. There is a number in physics called the Planck time. I think it is around 10 to the power of minus 43 seconds. Something like that. The exact figure is not what matters here. What matters is that it is a number so small that to write it as a decimal, you would need 42 zeros after the decimal point before you got to the 1. It is the smallest unit of time that our current physics can meaningfully describe. Smaller than the Planck time, our equations begin to fail. The two great theories we use to describe reality: general relativity, which describes gravity and the large-scale structure of space-time, and quantum mechanics, which describes the behavior of particles and fields at small scales, stop agreeing with each other below the Planck scale. They give inconsistent answers. Their predictions contradict. They stop being reliable guides to what is actually happening. This is not a temporary gap. It is not a failure of cleverness that will be fixed by a more careful calculation. It is, at least partly, a fundamental issue. The two theories rest on incompatible assumptions about the nature of space-time and reality, and reconciling them requires a new theory of quantum gravity that does not yet exist in fully verified form. When such a theory exists, it may tell us something about the very first moments. For now, the Planck time is a horizon we cannot see past with our current tools. Physicists sometimes describe space-time at the Planck scale as a kind of quant foam. The smooth, continuous fabric of space and time that we experience in everyday life, the arena in which things happen, the four-dimensional continuum of general relativity, is probably not smooth at the Planck scale. At those scales, quantum effects become important for space-time itself. The geometry of space fluctuates. Distances between points fluctuate. The normal concepts of smooth space and flowing time likely break down into something more turbulent, more uncertain, more like a froth than a fabric. What the universe was like at the Planck moment, at t equals 0, or rather at the smallest meaningful time after t equals 0, is unknown. Our equations approach this point from one side, but cannot describe it at the point itself. We call it a singularity, the place where the equations produce infinities and cease to give physically interpretable results. Not a physical object, a mathematical flag that says, the theory is reaching beyond its domain of validity. There are serious theoretical proposals about what might have preceded or surrounds the Big Bang. I want to describe a few because they are genuinely interesting and because they illustrate how thoughtful people approach a question that cannot currently be answered by observation. One is eternal inflation. This is the idea that our universe is not unique, that the inflationary process that expanded the very early universe is, in the larger picture, an eternal process. In this view, the inflaton field, the field responsible for inflation, never completely decays everywhere in the meta-universe. Instead, it persists in most of the volume, inflating eternally. Occasionally, in some small region, the inflaton field undergoes a quantum transition to a lower energy state, inflation ends locally, and a new universe bubbles off. Our Big Bang was one such bubble nucleation. Our universe is one bubble among perhaps infinitely many. Each bubble has its own physical constants, its own laws of physics, its own history. This is a serious scientific proposal with some theoretical support. It is also currently impossible to test directly. The other bubbles, other universes, are, by the nature of the model, beyond our observational horizon. We cannot reach them, see them, or interact with them. Some physicists find untestable proposals unscientific by definition. Others argue that if a well-supported theory makes predictions about unobservable domains, those predictions deserve serious consideration even without direct confirmation. Another proposal is the cyclic model, associated primarily with Paul Steinhardt and Neil Turok. In this picture, the universe oscillates. A Big Bang is followed by expansion, then eventually contraction, then another Big Bang, in a cycle that may have been repeating forever. Our universe is currently in an expansion phase. The Big Bang in our past was not an absolute beginning, but the latest in a potentially infinite sequence of beginnings. Modern versions of the cyclic model typically involve higher dimensional structures called branes, essentially membranes extended through additional spatial dimensions that periodically collide in a higher dimensional space. Each collision produces what looks, from within the resulting universe, like a Big Bang. The universe in this model is not a single bubble in a larger space, but a surface that periodically collides with another surface. Then there is the no-boundary proposal of Stephen Hawking and James Hartle. This takes a more radical approach. It uses the mathematics of quantum cosmology to suggest that the universe has no temporal boundary at all. In ordinary spacetime, time has a beginning, the Big Bang, and the initial singularity looks like an edge or boundary in time. But the no-boundary proposal, by treating time as a mathematical imaginary quantity in the context of quantum cosmology, smooths out this singularity. In the resulting picture, the universe is finite in time but has no boundary, no edge, no beginning in the conventional sense. Asking what happened before the Big Bang in this model is asking what lies south of the South Pole. The question seems grammatically well formed, but when you examine the geometry carefully, it turns out not to be asking anything coherent. I find this idea oddly calming to contemplate, not unsettling, calming, because it suggests the possibility that the universe is not missing anything, that it does not require something outside itself to explain it, that it just is complete and sufficient, the way a closed mathematical surface is complete and self-referential. Though I should be honest, none of these ideas has been confirmed. None can currently be directly tested. The honest scientific position is that we do not know what preceded the Big Bang, and we may never know, because inflation, the very process that made the universe so smooth and uniform and amenable to our observations, also erased most of the observational signatures of what came before it. The universe at its beginning is screened from our view by its own physics. This is, in its way, a beautiful kind of privacy. What we can say with genuine confidence, grounded in observations and carefully tested theory, is what the universe was doing at the Planck time and what it became shortly thereafter. We can describe the universe with precision and confidence all the way back to a tiny fraction of a second after the beginning. This is itself a remarkable achievement. The universe is 13.8 billion years old, and we can reconstruct its history from a tiny sliver of its very first second. The entire remainder of its existence, 13.8 billion years minus 1 microsecond, is, in principle, described by well-tested physics. The first microsecond is where it gets harder, but even there, we have good theoretical reasons to believe in the broad outline of what happened, even if some details remain uncertain. The temperature at the Planck time was the Planck temperature, roughly 10 to the 32 degrees Kelvin. I want to try to make this real rather than just a number. At 373 degrees Kelvin, the boiling point of water molecules have enough energy to escape each other's attraction and become steam. At a few thousand degrees, atoms shed their electrons entirely and become ionized plasma. At 15 million degrees, atomic nuclei fuse together in the reactions that power the sun. At 100 billion degrees, even atomic nuclei dissolve in the heat of a supernova's core. At 2 trillion degrees, protons and neutrons dissolve into their constituent quarks. 10 to the 32 degrees is 10 million billion times hotter than the temperature at which protons dissolve. At this temperature, every distinction that physics normally makes between particles and forces has been erased. The 4 fundamental forces, gravity, electromagnetism, the strong nuclear force, the weak nuclear force, are not 4 separate things. They are one, they are unified. A temperature at which the universe does not yet know how to be different things. That is the condition at the beginning. Everything unified, everything extreme. The universe in this state is a singularity in the mathematical sense, a place where our equations hit their limits and the usual rules of physics cease to apply reliably. But from this state, the universe began to evolve. Gravity separated first. At around the Planck time, gravity became distinct from the remaining unified force. The other 3 forces, electromagnetism, the strong nuclear force, the weak nuclear force, remained unified as what we call the grand unified force. The universe now had 2 forces instead of 1, already more differentiated than it was at the very beginning, already more complex. At around 10 to the minus 36 seconds, the strong nuclear force separated from the electroweak force. 3 forces now. And this separation, this symmetry breaking, released energy. It is thought to have triggered cosmic inflation, which we will come to shortly. The universe was already changing, already differentiating, already becoming richer and more complex with every fraction of a second. And the temperature was falling with every fraction of a second as well. Falling not because the universe was losing energy, but because the energy was being spread through a larger and larger volume as the universe expanded. The same amount of energy distributed across more space. That is how cooling works in an expanding universe. The total energy was conserved, the density fell, and with the density, the temperature. We are in the first microsecond. We are still in the first microsecond. But the universe has already undergone changes of staggering significance. It has gone from absolute unity, all forces one, all matter and energy undifferentiated, to a state with 4 distinct forces, a universe of particles and fields and the beginnings of structure. And in the next fraction of a second, it is going to do something that will shape everything that follows. Something quiet in the sense that it is not explosive or destructive. quiet in the way that a sudden exponential expansion of the fabric of space itself could be called quiet. Something that physicists, with characteristic understatement, call inflation. The temperature has fallen, the stage is set, the physics is ready, and the universe is about to do the strangest thing it will ever do. I want to try to describe the Planck era one more time, from a slightly different angle, because I think it is worth returning to before we leave it. At the Planck time, at that smallest meaningful moment, 10 to the minus 43 seconds, the universe was in a state where all four forces were unified. But what does that mean in a physical sense? Think about what the four fundamental forces do in the universe as it currently exists. Gravity holds the planets in orbit around the Sun, holds the Sun together against the pressure of its own fusion reactions, holds galaxies together, and shapes the large-scale structure of the cosmos. It is the weakest of the four forces, but operates over infinite range and always attracts. It never repels. Because it always attracts and never weakens to zero, it dominates at large scales. Electromagnetism holds atoms together. It is the force that keeps electrons orbiting nuclei. It is responsible for all chemistry, all biology, all the material interactions that make up the world of everyday experience. It is vastly stronger than gravity at small scales, but has both attractive and repulsive versions, which means that large objects with equal amounts of positive and negative charge tend to cancel out, limiting electromagnetism's role at large scales. The strong nuclear force holds the nuclei of atoms together. It binds the protons and neutrons into the compact nuclei at the heart of every atom. It is the strongest force known, enormously stronger than gravity or electromagnetism at the scales it operates. But it operates only over very short distances, roughly the size of a nucleus. Beyond a femtometer or so, it drops to zero. This is why atoms can exist. The protons in a nucleus are close enough together that the strong force binds them, but electrons orbiting far away do not feel the strong force significantly. The weak nuclear force governs certain types of nuclear reactions, particularly the beta decay processes that convert neutrons to protons, and vice versa. It is not weak in an absolute sense. It is much stronger than gravity, but it is weaker than the electromagnetic and strong forces at the energies of everyday physics. It also operates over very short ranges. These four forces, with their distinct properties and distinct ranges and distinct strengths, are the architecture of physics as we know it. Everything that happens in the universe, every interaction, every process, every transformation of matter and energy involves one or more of these forces. At the Planck temperature, they were one force. Not four forces that happen to have similar strengths, but genuinely one. A single interaction that, as the universe cooled and the symmetry broke, differentiated into four distinct things. The richness of physics as we know it, all the distinct phenomena arising from four different forces, was at the beginning a single unified phenomenon. This is not just a theoretical idea. We have partial evidence for it. The electromagnetic and weak forces were shown by Glashow, Weinberg, and Salam in the 1960s and 1970s to be unified at high energies, at energies above the electroweak scale, around 100 GeV, they become a single electroweak force. This unification is confirmed by experiments at particle accelerators. We can produce the conditions of the electroweak era in miniature at the Large Hadron Collider. The grand unified theories suggest that the strong force unifies with the electroweak force at much higher energies, around 10 to the 15 or 10 to the 16 GeV. This scale is far beyond any accelerator we can build or conceive of building, so direct experimental confirmation is not currently possible. But indirect evidence, the way the coupling constants of the three forces run with energy converging toward a common value at high energies, is suggestive. Gravity may unify with the other three forces at the Planck scale. This would require a theory of quantum gravity, which does not yet exist in fully verified form. But the mathematical machinery is being developed in theories like string theory and loop quantum gravity. Whether those theories are correct and what they predict about the Planck era remains an open question. So the story we are telling tonight, the story of the universe cooling from a state of complete force unification through a sequence of symmetry breakings to the four distinct forces we have today, is partly confirmed and partly theoretical. The electroweak unification is confirmed. The grand unification is not directly confirmed. The full unification at the Planck scale is a hypothesis, but the broad picture seems right. And the idea that the rich diversity of physical phenomena we observe, all the different forces and particles and interactions, emerged from a simpler, more symmetric beginning is one of the most beautiful and well-supported ideas in modern physics. From unity to diversity, from one force to four, from a state of perfect symmetry to the rich, complex, differentiated physics of the universe we inhabit. That is the story we have been setting up. And the first act of that story, the first great differentiation, the first expansion, the first moments of the cooling universe, is what we are about to describe: cosmic inflation. The word is almost absurdly understated for what it describes. In ordinary language, inflation means something getting a bit bigger. Prices rise a few percent. A balloon gets inflated with a breath of air. The tire on a car gets inflated with a pump. Things expand gradually, proportionally, in ways the mind can follow from cause to effect. Cosmic inflation was not that. Cosmic inflation was the universe expanding. In an almost unimaginably brief period, somewhere between 10 to the minus 36 seconds and 10 to the minus 32 seconds after the Big Bang, by a factor of at least 10 to the power of 26. The exact number depends on the specific version of inflation you are describing, and there are many versions. But the range is, the universe grew in that tiny fraction of a second, somewhere between 100 trillion times larger and potentially much larger than that. Let me try to make that concrete, because I think the abstract numbers deserve to be translated into something closer to feeling. A proton is roughly 1 femtometer across. A femtometer is 1/4,000th of a meter, so small that 100,000 protons lined up side by side would not span the width of a single atom. The atom, already invisible to any unassisted eye, is itself almost entirely empty space, a vast region compared to the nucleus at its center. Before inflation, the region of space that would eventually become the entire observable universe was smaller than a proton, smaller than 1 femtometer, smaller than the already almost incomprehensibly small nucleus of a hydrogen atom. After inflation, that same region was roughly the size of a grapefruit, maybe a marble, maybe something larger depending on the model. The exact post-inflationary size is uncertain, but even taking the conservative estimate of a marble or grapefruit, that is an expansion by a factor of something like 10 to the 25 or 10 to the 26. And it all happened in roughly 10 to the minus 32 seconds. To put this another way, the entire observable universe, which today contains hundreds of billions of galaxies, each containing hundreds of billions of stars, which spans roughly 93 billion light years in every direction, which contains all the matter and energy that has ever produced a star or a planet or a thought. All of that was, before inflation, compressed into a region smaller than a single proton. And in less time than any process we can currently measure, it expanded to something large enough to contain the seeds of all those galaxies. The idea of cosmic inflation was first proposed by a physicist named Alan Guth in 1980. Guth was a young researcher at the time, working through the theoretical implications of the early universe model, and he was bothered by several puzzles that the standard Big Bang picture could not satisfactorily resolve. Problems that looked, individually, like small cracks in the theory, but together suggested that something important was missing. The first of these puzzles was the horizon problem. When we look at the cosmic microwave background, the faint glow of the Big Bang's afterglow that fills the sky in every direction, we see that it is extraordinarily uniform. Its temperature is the same in every direction to about 1 part in 100,000. This uniformity is one of the most striking features of the observable universe. It would make sense if all the regions of the sky we are looking at had, at some point, been in thermal contact with each other, if they had been close enough together for long enough to exchange heat and reach the same temperature. But in the standard Big Bang model without inflation, this is not possible. The universe expanded so quickly after the Big Bang that regions on opposite sides of the sky were never in causal contact. Light never had time to travel between them. They were, from the very beginning, completely isolated from each other. So why do they have the same temperature? Inflation provides an elegant answer. Before inflation began, all the material that would become the observable universe was crammed into a tiny region, well within its own causal horizon. Everything in that tiny region could interact. Heat could flow. Equilibrium could be reached. The region smoothed itself out, thermalized, reached a uniform temperature. Then inflation stretched that tiny, smooth, equilibrated region across cosmic scales. The uniformity we observe in the cosmic microwave background is the uniformity of that original tiny patch written across the sky. The second puzzle was the flatness problem, the overall geometry of the universe, whether it curves positively like the surface of a sphere, negatively like a saddle, or lies perfectly flat, can be measured by observing the large-scale distribution of matter and the cosmic microwave background, and observations show that the universe is, to extraordinary precision, geometrically flat. In the standard Big Bang model, this is suspicious. Flatness is an unstable condition. In the evolving universe, any small deviation from perfect flatness would grow over time. The universe would become progressively more curved in whichever direction it started curving. To be as flat as we observe today, the universe would have had to be flat to 1 part in roughly 10 to the 60 at the very beginning. A fine-tuning so extreme it looks like the universe was set up, with extraordinary specificity, to be flat. Inflation solves this naturally. A rapidly inflating universe smooths out curvature. The extreme expansion stretches the geometry of space so dramatically that any initial curvature is diluted to insignificance. The same way a small balloon, which is visibly curved, becomes effectively flat when you blow it up enormously. Whatever curvature the pre-inflationary region had, inflation reduced it to negligibility. The third puzzle inflation solved was the absence of magnetic monopoles. Certain theories of particle physics, the grand unified theories that attempt to describe the strong force and electroweak force as aspects of a single unified interaction, predict that when the grand unified symmetry broke, it would have produced a large number of exotic particles called magnetic monopoles. These are hypothetical particles that would have a single magnetic pole, north without south, or south without north, and they are predicted to be very massive, roughly 10 to the 16 times the mass of a proton. In the standard Big Bang model, there should be roughly as many magnetic monopoles as there are protons. We should be surrounded by them. We have never detected a single one. Inflation solves this problem by dilution. If inflation occurred after the grand unified symmetry breaking, the enormous expansion would have diluted any monopoles that formed to an extreme rarity. The expected number of monopoles in the observable universe after inflation drops to something like 1 or fewer. We would never detect them. Their absence is not mysterious. It is predicted. 3 problems. 1 mechanism. This is the kind of theoretical elegance that makes physicists take an idea very seriously. But what actually drives inflation? The leading candidate is a field called the inflaton field. It is hypothetical. We have not directly detected the inflaton particle, the quantum of this field, but it is theoretically well motivated. The inflaton field in the early universe was in a high energy state, and the energy stored in this field had a property that ordinary energy does not. It acted as a repulsive cosmological constant. It drove space to expand, not the ordinary expansion driven by radiation and matter, which slows as the universe grows and the density falls, but an accelerating expansion that grew faster and faster as long as the inflaton remained in its high energy state. As the inflaton field slowly evolved, in the language of physics, as it slowly rolled down its potential energy curve toward a lower energy state, it continued to drive inflation. When it finally reached the ground state, the lowest energy state, inflation ended, and the energy that had been stored in the inflaton field was converted into particles and radiation in a process called reheating. The universe, after reheating, was filled with the hot, dense plasma of the post-inflationary Big Bang. The word reheating is slightly misleading. It suggests the universe was hot before inflation, cooled during it, and was then reheated. This is roughly correct, but worth clarifying. The energy driving inflation was not thermal energy in the ordinary sense. It was potential energy stored in the inflaton field. During inflation itself, the temperature of ordinary particle radiation was very low, because inflation had diluted everything. When the inflaton decayed at the end of inflation, that potential energy was converted into the kinetic energy of particles, and those particles thermalized. Their energies were distributed according to a thermal spectrum, producing the hot, dense, particle-filled universe of the post-inflationary period. And crucially, this is perhaps the most important thing inflation does. It does not produce a perfectly smooth universe. At first, you might think inflation would. Take a tiny region and stretch it uniformly. Wouldn't the result be uniform? In a purely classical picture, yes. But the early universe was quantum, and at the quantum level, perfect smoothness is impossible. The Heisenberg uncertainty principle, the fundamental rule of quantum mechanics that prevents you from simultaneously knowing everything about a system, ensures that quantum fields are always fluctuating. At the quantum level, there is always a minimum level of random variation. The inflaton field was no exception. During inflation, the inflaton field was subject to these quantum fluctuations. Random variations in the field, tiny, unavoidable, random patches of slightly higher and slightly lower energy, were present throughout the pre-inflationary region, and inflation took those quantum fluctuations and stretched them to cosmic scales. The slight overdensities, the patches where the inflaton was just fractionally higher, became, after inflation ended and reheating occurred, regions of slightly higher matter density. And those regions, over the following hundreds of millions of years, became the seeds of the cosmic web, the galaxies and galaxy clusters, and the vast filaments of matter that organize the observable universe. All of it traces back to those quantum fluctuations in the inflationary era. This is one of the most extraordinary facts in all of science. The large-scale structure of the universe. Everything we can see with our telescopes, the entire visible architecture of the cosmos, was seeded by quantum fluctuations during inflation, by the irreducible, unavoidable randomness that the laws of quantum mechanics build into every physical system at the smallest scales. The universe we inhabit is not just the product of inflation, but specifically of the quantum noise in the inflaton field during those first instants. Your existence traces back to quantum randomness. The galaxy that contains your solar system grew from an overdensity that grew from a quantum fluctuation. The particular neighborhood of the cosmic web in which you find yourself was, at its origin, just a random quantum hiccup in a tiny pre-inflationary field. We have observational evidence for this. The pattern of temperature fluctuations in the cosmic microwave background measured with extraordinary precision by the WMAP and Planck satellites, shows exactly the spectrum of fluctuations that inflationary models predict. The amplitude of the fluctuations, the way they are distributed across different angular scales, the statistical properties of the pattern, all of it matches inflation's predictions. Not perfectly, because the measurements are not yet precise enough to distinguish between different specific models of inflation, but in broad strokes the agreement is striking. Now, what does it mean for space to expand faster than light? This is worth addressing directly because it often causes confusion. Nothing moves through space faster than light. This is one of the most firmly established results in all of physics, confirmed by every experiment ever done. No particle, no signal, no information can move through space faster than c, the speed of light. But inflation is not about things moving through space. Inflation is about space itself expanding. The fabric of space stretched. 2 points in space moved apart, not because they travelled through space, but because the space between them grew. There is no limit in general relativity on how fast space itself can expand. This is why, today, distant galaxies are receding from us faster than light. Not because they are moving through space at superluminal speeds, but because the space between us and them is expanding. During inflation, the expansion was so rapid that adjacent regions of space were separated from causal contact faster than light could travel between them. This is what makes inflation so effective at solving the horizon problem. It's stretched the equilibrated, smooth pre-inflationary region across distances greater than light could ever cross, preserving that uniformity while making different regions causally disconnected. After inflation ended, at around 10 to the minus 32 seconds, the universe was vastly larger than before, and it was about to be filled with energy. The reheating process converted the inflaton field's energy into the hot plasma of particles and radiation that would characterize the universe's next phase. The temperature at reheating was around 10 to the 27 degrees Kelvin, a billion degrees. Every particle in the standard model of particle physics, quarks, leptons, bosons, and their antiparticles, was being created and annihilated in the plasma. Everything was in thermal equilibrium. Everything was interacting constantly. The universe was, in this moment, the most energetic environment that has ever existed in the history of the cosmos. And from this state, everything would follow. But we are still in the first microsecond. The quarks are free in the plasma, moving through the quark-gluon plasma that the hot post-inflationary universe has become. The forces are separating, with the electroweak force still to complete its separation. The temperature is falling with every passing moment as the universe expands, and something quiet is occurring in that plasma. Something that will, in the next fraction of a second, change the universe entirely. The quarks are about to find each other. They are about to bind. And in the binding, they will create the first protons and neutrons, the first seeds of all ordinary matter. But first they are still free, still swimming in the fire, still moving through the quark-gluon plasma in which the universe currently consists. And that plasma, in the fraction of a second before hadronization, is something worth understanding, because it is the last time the universe will ever be this simple. A single phase of undifferentiated matter, a sea of quarks and gluons flowing like a nearly perfect liquid in the extreme heat. After this moment, complexity accumulates. The universe will never be this uniform again. There is another aspect of inflation that deserves a moment of attention, because it is genuinely one of the strangest and most consequence-laden facts about the universe we inhabit. The inflationary expansion of the early universe was not uniform in time or space. In the simplest models of inflation, it ended at different moments in different regions of space, as the inflaton field decayed at slightly different times due to quantum fluctuations. The end of inflation the transition from the inflating vacuum energy dominated state to the hot particle-filled state of the post-inflationary universe happened everywhere in our observable universe at roughly the same time on cosmological scales. But in many inflationary models, inflation never completely ends. In most of the volume of the meta-universe, the larger space in which our bubble of ended inflation sits, the inflaton field persists and inflation continues. This is Alan Guth's eternal inflation scenario, which we mentioned briefly in the previous section. It has a startling implication. If inflation is eternal in most of the volume of the meta-universe, then new bubble universes are constantly being nucleated, constantly inflating from a point and expanding. Our universe is one such bubble. And in the vast majority of the volume of the meta-universe, the volume that is still inflating, conditions for new bubble nucleation are constantly occurring. The inflationary meta-universe in this picture is endlessly fecund. It produces bubble universes the way a pot of boiling water produces bubbles. Not all at once, not in any organized sequence, but continuously, irreversibly, in an ever-expanding foam of inflating regions, punctuated by pockets where inflation has ended, and something like our universe has formed. And each bubble universe, each pocket of ended inflation, may have its own physical constants. The specific values of the coupling constants, the particle masses, the cosmological constant. These may depend on the details of how the inflaton field decays in each bubble, different bubbles, different physical laws. This is the landscape of string theory, or the multiverse of eternal inflation, a vast collection of universes, each with its own physical constants, of which ours is one. We cannot see the other bubbles. They are beyond our cosmic horizon, separated from us by regions of still inflating space that light can never cross. We cannot test directly whether they exist, but the framework in which our universe is special among the possible universes has been deeply challenged by this picture. We are not the only universe. We may not be a typical universe. Our physical constants, the specific values that allow atoms and stars and life to exist, may be selected for, in some sense, by the fact that universes with different constants are not capable of producing observers who wonder about them. This is the anthropic principle in cosmology, and it is one of the most actively debated ideas in theoretical physics. Not everyone finds it satisfying. Many physicists find it explanatorily empty. It seems to explain anything by selecting for the conditions that allow the explanation to occur. Others find it genuinely illuminating. If there is a vast landscape of possible universes, the fact that we inhabit one with constants hospitable to life is no more mysterious than the fact that we live on a planet with the right temperature for liquid water. The debate is not resolved. It may not be resolvable with current physics, but knowing it exists, knowing that the question of why our universe has the specific physical constants it has is an open and actively contested question, is part of the honest picture of what science currently knows and does not know. What we do know is this: the inflation that happened in the first tiny fraction of the first second, whatever its ultimate status in the multiverse picture, set the stage for everything that followed in our universe. It made our universe flat. It made it smooth. It left the quantum fluctuations that seeded galaxies. It set the initial conditions from which the entire subsequent history of our universe developed. And that history developed from those initial conditions through the sequence of events we have been describing tonight into this, a cooling, expanding universe containing hydrogen and helium, and now all the elements, stars and galaxies and planets and life. And here, on planet, a person lying in the dark, thinking about inflation and the first microsecond and the atoms in their own cells. The inflation led here, indirectly through 13.8 billion years of cosmic development. But the path runs from that first fraction of a second to this moment, unbroken. There is a state of matter that existed in the universe's first microsecond and has not existed anywhere in the universe in any significant quantity since, called the quark-gluon plasma. It is exactly what its name suggests, and it is completely unlike anything that exists in the physical world today. Let me start with quarks because they deserve a proper introduction. Everything made of ordinary matter, every proton, every neutron, which means every atomic nucleus, which means every atom, which means every material thing in the universe that has mass in the conventional sense, is made of quarks. Quarks are, as far as we can currently tell, genuinely fundamental. They are not made of anything smaller. They are not composed of more basic constituents detectable by any instrument we have. They are among the most basic ingredients of the physical world, and they are strange in several ways that are worth understanding. There are 6 types of quark, which physicists call flavors: up, down, charm, strange, top, bottom. The names are essentially arbitrary, chosen by a community of physicists working in the 1960s and 1970s who were partly trying to amuse themselves. Nothing about a charm quark is charming in any sensory way. Nothing about a strange quark is particularly strange relative to its siblings. The names are historical accidents, preserved by convention. For our purposes, for the story of the first 10 minutes of the universe, the relevant quarks are the up quark and the down quark. These are the 2 lightest and most stable quarks. They are the quarks that make up the protons and neutrons that make up all ordinary matter. The other 4 quarks, charm, strange, top, bottom, were present in the quark-gluon plasma of the early universe, but they are unstable at ordinary temperatures and they decay quickly into lighter particles. Only the up and down quarks persist in stable form in the matter we encounter today. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 1 up quark and 2 down quarks. These are held together by particles called gluons, the quantum carriers of the strong nuclear force. Gluons do what their name suggests. They glue. They mediate the strong force, the strongest of the 4 fundamental forces, and their job is to keep quarks bound inside the particles that contain them. The strong nuclear force has a property that sets it apart from every other force in physics. It does not weaken as you try to separate the particles it binds. Gravity and electromagnetism both follow inverse square laws. The force between 2 objects decreases as the square of the distance between them increases. Get twice as far away, the force is 4 times weaker. The strong force does not behave like this. As you try to pull quarks apart, the strong force remains roughly constant or even increases. It is as if the quarks are connected by a rubber band rather than a spring. A spring weakens as it stretches. A rubber band stays taut, and if you stretch the rubber band far enough, it snaps. And when the strong force field snaps, the energy that was stored in it creates new quarks from the vacuum. You end up with 2 particles instead of 1 free quark. This is called quark confinement, and it is one of the defining features of QCD, quantum chromodynamics, the theory of the strong force. Under ordinary conditions, free quarks simply do not exist. They are always inside hadrons. They are always accompanied. The strong force does not allow them to be alone, except in the early universe, at the temperatures of the quark epoch, the thermal energy of the system was so enormous that confinement was overwhelmed. The quarks were so energetic, moving so fast, that the gluon fields between them could not keep up. Confinement ceased to operate. The quarks became free. Not entirely free, in the way that an electron in vacuum is free, but free in the sense that they moved through the plasma without being confined to individual hadronic particles. They flowed, they churned, they interacted with gluons and with each other in a collective, correlated way. This was the quark-gluon plasma. The universe existed in this state from shortly after the end of inflation until around 10 to the minus 6 seconds, 1 millionth of a second, after the Big Bang. This period is the quark epoch. To understand how extreme the conditions were, consider a temperature progression. The surface of the Sun sits at around 1800 degrees Kelvin. Warm, bright, hot enough to fuse nothing. Fusion requires the extreme density and temperature of the solar core, around 15 million degrees. A supernova's core reaches around 100 billion degrees, 10,000 times hotter than the solar core. And, at those temperatures, the nucleosynthesis of heavy elements can occur. 2 trillion degrees is the phase transition temperature of the quark-gluon plasma, the temperature at which protons and neutrons dissolve into free quarks. The quark epoch began at around 10 to the 15 degrees, 1,000 trillion degrees, 500 million times hotter than a supernova core. Even at the end of the quark epoch, the temperature had fallen only to around 2 trillion degrees, still 20 times hotter than a supernova. At these temperatures, ordinary matter in any form we would recognize simply does not exist. There are no atoms, there are no atomic nuclei, there are not even protons and neutrons. There is a sea of quarks and gluons, moving collectively as a near-perfect liquid, interacting constantly, exchanging energy through the strong force, in thermal equilibrium with the photons and leptons and other particles that fill the plasma, and not just quarks and gluons. The quark epoch plasma was a complete inventory of the standard model at high energy. Quarks in all 6 flavors, at least at the highest temperatures of the epoch, leptons, electrons, muons, taus and their neutrinos, moving through the plasma, photons in enormous numbers interacting constantly with the charged particles, the W and Z bosons, carriers of the weak nuclear force, still numerous at these temperatures, the Higgs boson present in abundance at the highest temperatures, everything in the standard model, all at once, all in equilibrium. The quark-gluon plasma was recreated in miniature in particle accelerator experiments on Earth. At the relativistic Heavy Ion Collider at Brookhaven National Laboratory in New York, and later at the Large Hadron Collider at CERN in Switzerland, physicists collided heavy atomic nuclei, gold nuclei at Brookhaven, lead nuclei at CERN, at very nearly the speed of light. The collision temperature, for a tiny fraction of a second, was high enough to dissolve the nuclei into a droplet of quark-gluon plasma. What those experiments found surprised everyone. The expected behavior was that of a weakly interacting gas. Quarks and gluons, moving more or less independently, interacting occasionally but mostly going their own way. What was actually observed was behavior more like a liquid, a strongly correlated, collective flow. The quark-gluon plasma turned out to have the lowest viscosity of any substance ever measured, lower than liquid helium, lower than any ordinary liquid. A nearly perfect fluid in the technical sense of having a viscosity close to the theoretical minimum allowed by quantum mechanics. This means the early universe in its first microsecond was not a chaotic gas. It was a flowing, collective, strongly correlated liquid. The universe's most primitive state was also, in a sense, one of its most orderly states, not structured in the way a crystal is structured, but coherent in the way a flowing river is coherent, organized at the microscopic level even in the absence of any macroscopic structure. This is, in retrospect, perhaps not surprising. The universe has never been truly simple. Even at its most primitive, its physics was rich, and its behavior collective. Now, something else was happening in this plasma that would determine the fate of everything. At the temperatures of the quark epoch, particle-antiparticle pairs were being constantly created from the thermal energy of the plasma and constantly annihilating back into it. For every quark that the thermal energy produced, an antiquark was also produced, because the fundamental interactions of particle physics conserve all the relevant quantum numbers, and creating a particle without creating its antiparticle is not permitted. So the plasma contained, for every quark, very nearly one antiquark, for every electron, very nearly one positron, for every neutrino, very nearly one antineutrino, very nearly, but not exactly. There was, for reasons that physics has not yet fully explained, a tiny asymmetry. For every billion antiquarks in the plasma, there were 1,000,000,001 quarks. One extra quark for every billion pairs. This asymmetry, this tiny imbalance between matter and antimatter in the very early universe, is called baryogenesis. It is one of the deepest unsolved problems in physics. We know the asymmetry was there because we exist. If matter and antimatter had been exactly balanced, they would have annihilated each other completely, and the universe would contain nothing but radiation. No atoms, no stars, no galaxies, no people. The existence of matter at all is proof that the asymmetry existed. We know roughly how large the asymmetry was, about 1 part in a billion, because we can measure the ratio of photons to baryons in the current universe, and that ratio reflects the ratio that would have been left after the Great Annihilation. What we do not fully know is why the asymmetry existed. The conditions required for matter-antimatter asymmetry to develop in the early universe were worked out theoretically by the Soviet physicist Andrei Sakharov in 1967. Sakharov identified 3 conditions, now called the Sakharov conditions, that are necessary for any process to generate a matter-antimatter asymmetry. The conditions are baryon number violation. Processes that create more baryons than antibaryons must be possible. C and CP violation. The laws of physics must distinguish between matter and antimatter in certain ways, and departure from thermal equilibrium. The universe must be out of equilibrium at the relevant time. These conditions can all be satisfied, in principle, by the physics of the Standard Model and its extensions. But the Standard Model does not produce enough asymmetry on its own. The asymmetry it generates is far too small, by many orders of magnitude, to explain the observed matter-antimatter ratio, which means that something beyond the Standard Model was responsible for baryogenesis. Something that physics has not yet identified with certainty, the search for the mechanism of baryogenesis, for the physical process that created that 1 extra quark for every billion pairs, is one of the active frontiers of particle physics and cosmology. It is the search for the reason we exist, in a very literal sense. Right now, in the atoms in your hand, the hydrogen in the water in your cells, the oxygen bonded to that hydrogen, the carbon in your organic molecules, every atom exists because of that 1 in a billion asymmetry. You are made of the tiny residue that was left over after the universe destroyed its own matter in the great matter-antimatter annihilation. You are the rounding error, the remainder, the 1 extra quark for every billion that got thrown away, and somehow that is not a diminishing thought. Somehow, at this hour, in this quiet, it feels like the opposite, that you are here at all, that anything is here at all, is the result of a tiny asymmetry that physics cannot yet fully explain. That is not a gap in the story. It is a door that is still open. The universe kept a little of itself, and that little is everything. The quark epoch was winding down. The temperature was falling. 10 to the minus 12 seconds had become 10 to the minus 9 seconds, had become 10 to the minus 6 seconds, a millionth of a second. The temperature fell from thousands of trillions of degrees to just around 2 trillion degrees. And at 2 trillion degrees, confinement reasserted itself. The gluon interactions between quarks, the rubber bands that the extreme heat had been holding taut, began to pull the quarks together. The thermal energy that had kept the quarks free was no longer sufficient to overcome the strong force. Quarks began to bind into hadrons. 2 up quarks and a down quark found each other and became a proton. 1 up quark and 2 down quarks found each other and became a neutron, and many other combinations, producing heavier and more exotic hadrons that would quickly decay. This was hadronization, the QCD phase transition. The moment the quark-gluon plasma froze into a gas of hadrons, and in the hadron gas that resulted from this transition, protons and antiprotons, neutrons and antineutrons existed briefly together, before very quickly finding each other, before the great annihilation swept through. Proton meets antiproton, neutron meets antineutron, both pairs annihilate into photons. The hadronic matter that had formed from the quark-gluon plasma almost entirely destroyed itself in the moments following hadronization. A billion protons met a billion antiprotons and became radiation. A billion neutrons met a billion antineutrons and became radiation. And the one proton that had no antiproton to meet, the one extra, the product of baryogenesis, the rounding error, that one survived. That one proton and its companions in the surplus matter are the ancestors of every atom in the universe. The universe at the end of the Hadron epoch was almost entirely radiation. Photons, an ocean of light, and swimming in that ocean in unimaginable numbers but constituting a tiny fraction of the total energy of the universe, the surviving protons and neutrons, cold compared to what had come before. Lonely, in a sense, the only matter in a universe almost entirely made of energy. But patient, the protons would survive. And in the minutes ahead, the next few minutes, the minutes we will reach in the second part of tonight's journey, they would do something extraordinary with their survival. They would make elements. The first elements that would ever exist. From scratch. From scratch in the furnace of the early universe. And those elements, hydrogen, helium, a trace of lithium, would be the materials from which everything else was eventually built. The recipe for all of that is still ahead, in the cooling fire of the next few minutes, in the first nucleosynthesis, in the first chemistry of the cosmos. But for now, the quarks have found each other. The first protons are forming. The matter-antimatter annihilation is sweeping through the young universe. And what will remain when it is done is the raw material of everything. The beginning of matter in the truest sense, waiting in the cooling fire for what comes next. The universe, at the end of the Hadron epoch, was almost entirely light. Not light in the gentle sense, not the warm amber of a lamp or the blue-white of a clear morning. Light in the physicist's sense. Photons, electromagnetic radiation. An ocean of energy moving in every direction at the speed of light, filling the expanding universe with a brilliance that no eye could have survived. In a space where there were no eyes and would not be for a very long time. And in that ocean of photons, swimming in almost unimaginable numbers, but constituting a tiny, tiny fraction of the total energy of the universe, were the survivors. Protons, neutrons, the lightweight particle called the electron, and its ghostly companion, the neutrino. These were the remnants of matter after the great annihilation. After every proton had met its antiproton, after every neutron had met its antineutron, after every electron had met its positron, and both had converted back to radiation, these were what was left, the residue, the 1 in a billion. The universe had tried, in a sense, to erase itself. The symmetry between matter and antimatter, if perfect, would have produced a universe of pure radiation. No atoms, no stars, no anything material. Just an expanding ocean of photons, growing colder and more diffuse as the universe expanded for billions of years, until they were too spread out and too cold to interact meaningfully with anything. Nothing would ever have formed. Nothing would ever have thought about the universe. Nothing would have been here to wonder about any of this. But the symmetry was not perfect, and the reason it was not perfect is one of the deepest open questions in all of physics. Let me describe what we know and what we do not, because both are important. What we know, the asymmetry existed. We can prove this simply by existing. If there had been no excess of matter over antimatter, we would not be here to notice. The fact of our existence, the fact of any matter at all in the current universe, is direct evidence that the early universe contained more matter than antimatter. We can also constrain the size of the asymmetry. The current universe contains roughly 1 billion photons for every proton. That ratio, 1 baryon for every billion photons, reflects the conditions of the early universe after matter and antimatter annihilated. For every billion matter-antimatter pairs that annihilated into 2 photons each, there was 1 extra particle of matter. That matter survived. The photons from the annihilation are still around. They are part of the cosmic microwave background, the vast sea of photons that fills the universe today. So we know the asymmetry was approximately 1 part in a billion, 1 extra quark for every billion quark-antiquark pairs. What we do not fully know is what caused it. The conditions required for any physical process to generate a matter-antimatter asymmetry were worked out by the Soviet physicist Andrei Sakharov in 1967. Sakharov was one of the most remarkable scientists of the 20th century, a theoretical physicist who made fundamental contributions to cosmology, and also a dissident who spent years in internal exile for his opposition to the Soviet government. He identified 3 conditions, now called the Sakharov conditions, that any baryogenesis mechanism must satisfy. First, baryon number violation. Baryon number is a quantity that counts the number of baryons, particles like protons and neutrons made of 3 quarks, minus the number of antibaryons. In ordinary particle physics, as we know it at low energies, baryon number is conserved. Protons do not spontaneously turn into other things. But for baryogenesis to generate an asymmetry, there must be processes that violate baryon number conservation, processes that can create more baryons than antibaryons or vice versa. Second, C and CP violation. C symmetry is charge conjugation, the symmetry between particles and antiparticles. CP symmetry is charge conjugation, combined parity, which is the symmetry between mirror images. If the laws of physics were perfectly C or CP symmetric, any process that generated more baryons would be exactly balanced by a process that generated more antibaryons, and no net asymmetry would develop. The laws of physics must treat matter and antimatter differently for baryogenesis to work. We know that CP violation exists. It has been observed experimentally in the decays of certain exotic particles, kaons and B mesons. The standard model of particle physics includes CP violation as a feature of the weak interaction, but the amount of CP violation in the standard model is far too small to explain the observed matter-antimatter asymmetry. By many orders of magnitude, this is one of the clearest indications that physics beyond the standard model exists. The known physics cannot explain why we exist. Third, departure from thermal equilibrium. In perfect thermal equilibrium, forward and reverse reactions occur at the same rate. Any process that created baryons would be exactly balanced by its reverse. For a net asymmetry to develop, the universe must have been out of equilibrium at the relevant time, which, in an expanding and cooling universe, is not difficult to achieve at phase transitions. All 3 conditions can be satisfied in principle, but the standard model does not satisfy them in the right amounts. Something beyond the standard model, some physics we have not yet discovered, was responsible for the process that made matter more abundant than antimatter in the early universe. This is, I think, one of the most extraordinary facts about our existence. The reason you are here, the reason anything material exists, is a physical process that we do not yet fully understand. The mechanism that tilted the universe in favor of matter over antimatter, that produced the 1 extra quark for every billion pairs, is unknown. It is one of the active frontiers of physics. People are working on it right now, running experiments, building theories, searching for the signature of the process in data from particle colliders and neutrino detectors and cosmic ray observatories. And we do not yet know the answer, which means that the deepest question about why you exist why matter exists at all rather than just radiation, is still open. That openness is not a failure. It is an invitation. An honest acknowledgement that the universe still seeks secrets, that physics still has frontiers, that there are questions the human mind has not yet answered. And somehow, in the dark and the quiet, that feels like a good thing to know, that we are not yet finished with the universe, that the universe is not yet finished with us. But set that mystery aside for now, because the story does not stop there. The asymmetry existed. Whatever caused it, the matter survived, whatever the mechanism. And in the minutes following the matter-antimatter annihilation, the surviving matter, the 1 in a billion residue, was in a universe that was cooling rapidly. Let me describe what the universe looked like at the end of the Hadron epoch, around 1/100th of a second after the Big Bang. The temperature was around 100 billion degrees Kelvin. That is still incomprehensibly hot by any ordinary measure, 10,000 times hotter than a supernova core. But it was cold compared to what had come before. The universe had already cooled by many orders of magnitude from its initial extreme temperatures. The matter present consisted mostly of protons and neutrons in very nearly equal numbers. The ratio was not quite equal. There were slightly more protons than neutrons, for reasons we will examine shortly. But roughly speaking, for every proton there was a neutron. There were also electrons in numbers equal to the number of protons, since the universe had to be electrically neutral overall, and there were neutrinos, vast numbers of neutrinos, moving through the plasma, interacting with matter through the weak nuclear force, and photons, the dominant component of the universe's energy at this time, vastly outnumbering the matter particles. The universe was a hot, dense, expanding gas of protons, neutrons, electrons, neutrinos, and photons, and it was still cooling. And as it cooled, something remarkable was about to happen to the ratio of protons to neutrons. Because that ratio, the balance between these two particles, each of which is made of 3 quarks but arranged differently, would determine the composition of the universe. It would determine how much hydrogen and how much helium the universe would contain. And those abundances, set in the first few minutes, would persist essentially unchanged for billions of years, still visible in the oldest, most primitive stars in the universe, still describable by the same physics. Still confirming the story of the first minutes every time an astronomer measures the spectrum of a distant quasar. But we are getting slightly ahead. The proton-neutron ratio has not yet been set. It is still evolving. And to understand how it is evolving, we need to understand the weak nuclear force. The weak nuclear force is the least familiar of the 4 fundamental forces in everyday experience, but it is crucial for the story of the early universe. It is responsible for certain types of radioactive decay, specifically beta decay, in which a neutron turns into a proton, emitting an electron and an antineutrino. The reverse process also occurs. A proton can turn into a neutron, absorbing an electron neutrino, in a process called inverse beta decay. In the hot, dense early universe, with the thermal energy available, these interconversions between protons and neutrons were occurring constantly. A neutron would decay into a proton would capture a neutrino and become a neutron, forward and back, constantly. The ratio of protons to neutrons was determined by the balance between these forward and reverse reactions. Now, there is a slight difference in mass between the proton and the neutron. The neutron is slightly heavier, by about 1.3 MeV, or about 0.14%. This mass difference means that in thermal equilibrium at high temperatures, when the thermal energy available is much larger than this mass difference, protons and neutrons are equally likely. The ratio is close to 1:1, but as the universe cooled, the thermal energy available decreased. And when the thermal energy approached the mass difference between the proton and neutron, the equilibrium began to shift. The neutron is heavier. Creating a neutron requires more energy. As thermal energy fell, fewer neutrons could be created. The ratio began to shift in favor of protons. At around 1 second after the Big Bang, the temperature had fallen to roughly 10 billion degrees Kelvin. And something important happened at this point. The neutrinos decoupled. At temperatures as above roughly 10 billion degrees, neutrinos were interacting frequently enough with electrons and protons and neutrons that they were in thermal equilibrium with the rest of the plasma. They were part of the same system. Their interactions were maintaining the balance between protons and neutrons. At around 10 billion degrees, the universe had expanded enough that the density was low enough that neutrino interactions became too infrequent to maintain equilibrium. The neutrinos decoupled from the rest of the matter. They stopped interacting significantly and began to stream freely through the universe, essentially unimpeded. This is called the neutrino decoupling, and it marks an important transition. After neutrino decoupling, the interconversions between protons and neutrons slowed dramatically. The ratio of protons to neutrons was, in a sense, frozen in at the value it had reached by the time of decoupling. At the moment of neutrino decoupling, the proton-to-neut ratio was roughly 5:1. For every 5 protons, there was 1 neutron, but even after decoupling, the ratio continued to drift slightly for a different reason. Free neutron stable. A neutron by itself, not inside a nucleus, will decay into a proton, an electron, and an anti-neutrino with a half-life of around 10 minutes. Left alone, free neutrons disappear. So between neutrino decoupling at around 1 second and the time when neutrons were incorporated into atomic nuclei at around 1 to 3 minutes, the free neutrons were slowly decaying. By the time nucleosynthesis began, the proton-to-neutron ratio had shifted from roughly 5:1 at decoupling to roughly 7:1. 7 protons for every neutron. That ratio, 7:1, would determine the composition of the universe for the rest of time. Hold that number. We will come back to it when we get to the nucleosynthesis, when we see exactly how 7:1 translates into the universe being 75% hydrogen and 25% helium by mass. When we see how those first minutes locked in a composition that remains measurable in the oldest stars today. But before we get to nucleosynthesis, there was one more crucial transition, one more separation, one more cooling milestone. At around 1 second, in addition to neutrino decoupling, the electrons and positrons were still annihilating. The last of the antimatter was meeting the last of the matter in that great annihilation, and the electrons, like the quarks before them, were also subject to the 1 in a billion asymmetry of matter over antimatter. Enough electrons survived, 1 per proton, to maintain charge neutrality, and the positrons were swept away in the annihilation. The universe at 1 second was a simpler place than it had been a second before. The proton-to-neutron ratio was shifting towards 7:1. The photons and surviving matter were moving forward together, and at around 1 second the universe crossed another threshold. The temperature fell below the energy at which neutron-proton interconversions were efficient. The ratio was freezing in. Not yet locked, neutrons were still slowly decaying, but the trend was set. Matter had won, not triumphantly, not dramatically, quietly, in the same way that a tide goes out, gradually, steadily, without announcement. Matter had won, and in winning it had set the stage for everything that would ever exist, for the stars and the planets and the lives and the minds that would eventually, 13.8 billion years later, look back and try to reconstruct what had happened in these first extraordinary seconds. The universe at 1 second was cooling fast, moving fast through the temperatures at which each new milestone was crossed. And the next milestone, the one that would lock in the composition of the universe permanently, was coming up fast. Big Bang nucleosynthesis, the moment when the protons and neutrons would bind together, when the first atomic nuclei would form, when the universe would make its first real chemistry, and everything that follows, every element, every molecule, every star, every cell, every thought, would grow from that chemistry. The fire is cooling, the protons and neutrons are waiting, and the first atoms are almost here. At 1/10,000th of a second after the Big Bang, the universe contained its first protons and neutrons. And, for the next few seconds, the seconds between the end of the Hadron epoch and the beginning of nucleosynthesis, those protons and neutrons existed in a state of anxious equilibrium, converting back and forth between each other through the weak nuclear force, their ratio slowly, inevitably shifting toward the value that would determine the composition of everything that followed. This is worth sitting with for a while. The proton is one of the great objects of the universe, one of the most stable, one of the most abundant. Protons have been around for 13.8 billion years and show no sign of decaying. The experimental lower bound on the proton lifetime is around 10 to the 34 years, which is enormously longer than the current age of the universe. Protons appear, as far as we can tell, to be essentially permanent. The universe's matter is substantially made of them, and yet the proton is not simple. It is easy to say a proton is two up quarks and a down quark, and that is true, but the reality is considerably richer. The quarks inside a proton are not sitting still. They are moving extremely fast, bound by the strong nuclear force into a tiny volume of about 1 femtometer cubed, constantly exchanging gluons, constantly surrounded by a sea of virtual quark-antiquark pairs popping in and out of existence. The interior of a proton is a turbulent, dynamic, intensely energetic place. Most of the proton's mass, around 938 MeV, where MeV is a unit of energy mass, does not come from the masses of the quarks themselves. The up and down quarks that constitute the proton each have masses of just a few MeV. Add up the bare quark masses, and you get perhaps 10 MeV total, but the proton weighs 938 MeV. The rest of the mass, about 99% of it, comes from the energy of the interactions inside the proton, from the kinetic energy of the quarks moving around at high speed, from the energy stored in the gluon fields binding them, from the energy of the virtual quark-antiquark pairs in the sea. This is mass created from energy, exactly as Einstein's equation E equals mc² describes. The proton is, in a very real sense, mostly interaction energy that has been given form and confined to a small space. It is a kind of crystallized fire, a small, stable package of the enormous energy of the strong nuclear force, organized by the laws of quantum chromodynamics, into something that can persist for trillions of years. And it is, in a sense, the first great achievement of the early universe, the first stable structure, the first object that the universe made that has lasted. The neutron, its companion particle, is structurally very similar. 1 up quark and 2 down quarks, bound by the same gluons. Its mass is slightly higher than the proton, 939.6 MeV versus 938.3 MeV for the proton. And unlike the proton, the free neutron is unstable. Left alone outside a nucleus, a neutron will decay in about 10 to 15 minutes. More precisely, with a half-life of around 610 to 614 seconds, depending on the most recent measurements. It decays into a proton, an electron, and an electron antineutrino. This instability of the free neutron was crucial to the story of the first few minutes. When neutrinos decoupled from the rest of the plasma at around 1 second after the Big Bang, when the universe cooled to around 10 billion degrees, the reactions that converted protons and neutrons back and forth froze out. Not instantly, but over a short period, the rate of interconversions dropped to negligible levels. The ratio of protons to neutrons was roughly 5 to 1 at that point. But then the free neutrons began to decay. Over the following seconds and minutes, the time between neutrino decoupling and the onset of nucleosynthesis, Free neutrons decayed into protons. The ratio drifted from 5 to 1 towards 7 to 1. By the time the temperature fell low enough for deuterium, the first nuclear-bound state, to become stable and persist, the ratio was approximately still 7 protons for every 1 neutron. The physics that set this ratio is, in retrospect, beautifully determined. The proton-to-neutron ratio at nucleosynthesis depends on 3 things: the mass difference between the neutron and proton, the number of nucleotypes, and the rate at which the universe was expanding at the time of neutrino decoupling. Change any of these and the ratio changes. Change the ratio and the composition of the universe changes. Change the composition of the universe and the stars are different. The stellar processes are different. The elements they produce are different. And everything downstream is different. The 3 neutrino types. This is interesting. We know from particle physics that there are 3 types, or generations, of neutrino corresponding to the 3 generations of leptons: electron neutrinos, muon neutrinos, and tau neutrinos. All 3 contribute to the energy density of the early universe, and the energy density determines the expansion rate, and the expansion rate determines when the neutrinos decouple, and that timing determines the proton-to-neutron ratio. If there were 4 generations of neutrino instead of 3, the expansion rate would be slightly faster. Decoupling would occur slightly earlier. The ratio at decoupling would be slightly different. And the composition of the universe, the fraction of helium versus hydrogen, would be slightly different by a measurable amount. And this is one of the extraordinary things about Big Bang nucleosynthesis as a probe of physics: the observed composition of the universe. The ratio of hydrogen to helium in the oldest, most primitive astronomical objects is consistent with exactly 3 generations of neutrino. Not 4, not 2, 3. We knew there were 3 generations of neutrino from particle accelerator experiments, but we also know it from the composition of the universe, as set in the first few minutes. The 2 methods agree. This is a remarkable consistency check, a place where the physics of the very early universe and the physics of the particle accelerator give the same answer by completely independent routes. The universe in those first minutes was performing an experiment that we can still read the results of today. Now, let me describe what was happening in the universe between 1 second and about 100 seconds. The period when the proton-to-neutron ratio was being set. The temperature was around 10 billion degrees at the start of this period and falling fast. The universe was a plasma, a dense hot gas of protons, neutrons, electrons, and photons, all moving rapidly, all interacting. The photons were the dominant component by energy, but the matter particles were present in enormous absolute numbers. The protons and neutrons in this plasma were colliding constantly. At these temperatures, they had enough energy to be close to each other, to be within range of the strong nuclear force. But they were moving too fast for the strong force to hold them together. Whenever 2 nucleons, proton or neutron, came close enough that the strong force was operating, the thermal energy was enough to pull them apart again before a bound state could form. Think of it like trying to stack 2 magnets when they are being constantly jostled. If the jostling is violent enough, the magnets cannot stick. The strong nuclear force was trying to bind the nucleons, but the thermal energy was too high. Every time a proton and neutron got close enough to begin forming a bound state, a deuterium nucleus, a high-energy photon would come along and break it apart. This is called the deuterium bottleneck. Deuterium is the simplest nucleus, more complex than a lone proton. It consists of 1 proton and 1 neutron bound together by the strong nuclear force. It is the first rung on the ladder of nuclear complexity. Without tight deuterium forming and persisting, nucleosynthesis cannot proceed. The heavier nuclei that form from deuterium cannot develop. The binding energy of deuterium is relatively low, about 2.2 MeV. This means that a photon with an energy of 2.2 MeV or more can break deuterium apart. And in the hot early universe, photons of that energy were abundant. So every deuterium nucleus that formed was quickly blasted apart by the ambient radiation. Deuterium formation was the bottleneck. The neutrons were waiting, slowly decaying, slowly disappearing, while the universe cooled toward the temperature at which photons of sufficient energy became rare enough that deuterium could persist. The temperature at which this occurred, the temperature at which the universe finally became cool enough for deuterium to survive, was around 1 billion degrees. This corresponds to a time of around 100 seconds, just under 2 minutes after the Big Bang. When the universe crossed this threshold, the deuterium bottleneck broke open. Suddenly, the deuterium nuclei that formed were not immediately blasted apart. They persisted, and once deuterium was persisting, the next reactions could occur. Deuterium could capture another neutron to make tritium, or another proton to make helium-3. Tritium could capture a proton to make helium-4. Helium-3 could capture a neutron to make helium-4. And helium-4, the alpha particle, 2 protons and 2 neutrons tightly bound, is extraordinarily stable. Its binding energy per nucleon is much higher than deuterium or tritium or helium-3. Once helium-4 forms, it is very difficult to break apart. It is, under the conditions of the early universe, essentially a one-way street. The universe, in those first few minutes after the deuterium bottleneck opened, rushed to make helium-4. Every available neutron was rapidly incorporated into helium-4 nuclei. And this is where the 7-to-1 ratio becomes the composition of the universe. At the onset of nucleosynthesis, there were 7 protons for every neutron. For simplicity, take 14 protons and 2 neutrons, maintaining the 7-to-1 ratio in small numbers. The 2 neutrons each pair with a proton to form a helium-4 nucleus. That requires 2 neutrons and 2 protons. The helium-4 nucleus is formed. The remaining 12 protons stay as protons, as hydrogen nuclei, lone protons without a neutron to pair with. So we have one helium-4 nucleus containing 2 protons and 2 neutrons with a mass of 4 units, and 12 hydrogen nuclei, each containing 1 proton with a total mass of 12 units. Total mass of helium, 4. Total mass of hydrogen, 12. Total mass, 16. Helium fraction by mass, 416, 25%. Hydrogen fraction by mass, 1216, 75%. 75% hydrogen, 25% helium. This is the composition of the universe after Big Bang nucleosynthesis. And this is, with remarkable precision, the composition that astronomers observe in the oldest, most primitive stars. Stars that formed from gas that had not been significantly processed by stellar nucleosynthesis, that still carries the composition of the primordial universe. The numbers match. The prediction of Big Bang nucleosynthesis matches the observation of the oldest stellar spectra. This match, this agreement between theory and observation, calculated from first principles using the physics of the first few minutes, and confirmed by measurements of stars billions of light years away, is one of the most powerful confirmations in all of cosmology. The universe told us, in the composition of its oldest stars, the story of its first minutes, and we listened, and the story was right. This is where we are going next, into those first minutes, into the nucleosynthesis itself, into the extraordinary few minutes when the composition of the universe was set for the rest of time. But before we get there, let me say one more thing about protons. You have roughly 7 times 10 to the 27 protons in your body. That is a 7 followed by 27 zeros. 7 billion billion protons. Each one of them was made in the process we have been describing, in the cooling quark-gluon plasma of the first microsecond, in the binding of quarks at the end of the quark epoch. Each one of them survived the matter-antimatter annihilation because of the 1 in a billion asymmetry that physics cannot yet fully explain. Each one of them waited in the proton-neutron equilibrium of the first second, while the weak nuclear force and the thermal energy of the universe negotiated the ratio that would determine the composition of everything. 7 billion billion protons in you, each one a tiny crystallized remnant of the earliest universe, each one participating right now in the biochemistry of your body, in the hydrogen bonds that hold your DNA's double helix together, in the ionic gradients that allow your neurons to fire, in the acid-base chemistry of your blood. The universe made those protons in its first microsecond. They have been doing things ever since, including, for a few hours tonight, being at rest. The proton-to-neutron ratio was not only crucial for the composition of the universe, it was also a prediction that could be tested against real observations, and it has been tested repeatedly in the oldest material we can find. In the 1960s and 1970s, physicists began to understand that the light element abundances in the universe could be used as a direct probe of the first minutes. If Big Bang nucleosynthesis theory was correct, the primordial abundances of hydrogen, helium, deuterium, helium-3, and lithium should have specific values determined by the physics of the first few minutes. Measure those abundances in old, pristine material, in ancient stars or intergalactic gas clouds, least processed by subsequent stellar chemistry, and you could test whether the theory was right. This is a remarkably elegant idea. We cannot visit the early universe. We cannot set up instruments in the plasma of the first minutes, but the products of that plasma are still around, preserved nearly unchanged for 13.8 billion years in the most chemically primitive environments we can find. By measuring those environments with spectroscopes on large telescopes, we can read the record of the first minutes. The helium abundance was the first to be measured. Old, metal-poor galaxies and globular clusters, environments where stellar processing has been minimal, show helium fractions by mass of around 24 to 25%. In agreement with the prediction, small variations between different environments can be used to extrapolate to the true primordial value, and the result is consistent with the 25% predicted by Big Bang nucleosynthesis theory. Deuterium is in some ways the most sensitive probe. Its primordial abundance depends steeply on the baryon density in the early universe. More baryons means more complete burning of deuterium into helium and a lower surviving deuterium fraction. Less baryons means higher surviving deuterium. By measuring the primordial deuterium abundance, astronomers can constrain the baryon density of the early universe. The best measurements of primordial deuterium come from observations of very distant, ancient gas clouds that happen to lie along the line of sight to even more distant quasars. The quasar's light passes through the gas cloud and is absorbed at specific wavelengths by hydrogen and deuterium in the cloud. By comparing the hydrogen and deuterium absorption features, astronomers can measure their ratio directly. These measurements give a primordial deuterium to hydrogen ratio of about 2.5 parts in 100,000, consistent with theoretical predictions. The agreement between theory and observation across multiple independent measurements is one of the most powerful confirmations of the Big Bang model. It is not approximate agreement. It is quantitative agreement, specific numbers predicted by theory, confirmed by independent measurements made with different instruments measuring different things. And all of it traces back to the proton-to-neutron ratio, to the 7:1 ratio set by the first second, to those protons and neutrons forming from the quark-gluon plasma, their ratio shifting in the cooling plasma. Patient as physics can be patient, heading toward the extraordinary 10 minutes that would lock in the composition of everything. The window was opening, the deuterium bottleneck was about to break, and the universe was about to make its first real chemistry. There is a book by the physicist Steven Weinberg, published in 1977, called The First 3 Minutes. Weinberg was one of the architects of the electroweak theory, one of the physicists who showed that electromagnetism and the weak nuclear force were two aspects of a single unified interaction, work for which he shared the Nobel Prize in Physics in 1979. And in this book, he set out to describe, for a general audience, what the universe was doing in the first 3 minutes of its existence. The book opens with a statement that has stayed with many readers. Weinberg writes that the more the universe seems comprehensible, the more it also seems pointless. He was being honest about a feeling that scientific understanding sometimes produces, that explaining something beautifully and completely does not automatically reveal a purpose behind it. I think about that sentence sometimes, and I think that whether you find the universe pointless or not may depend on where you stand when you look at it. From one angle, a universe that produced you through a series of physics events without intention or design might seem cold and indifferent. From another angle, the angle we have been taking tonight, a universe that organized itself from a hot plasma into something capable of wondering about itself seems, if not purposeful exactly, then at least extraordinary, quietly extraordinary. But let's set that aside and go into the 3 minutes themselves, because they are remarkable regardless of what you decide about their significance. At roughly 1 second after the Big Bang, the temperature was around 10 billion degrees. Neutrinos had just decoupled. The matter-antimatter annihilation of electrons and positrons was finishing up. The universe was full of protons, neutrons, electrons, neutrinos, and photons. The proton-to-neutron ratio was approximately 5:1 at this moment, and it was drifting slowly towards 7:1 as free neutrons decayed. The expansion was continuing. The temperature was falling. At 10 billion degrees, the thermal energy was still far too high for deuterium to form and survive. Let me try to describe what a second in this context actually means. At 1 second after the Big Bang, the rate of change in the universe was extraordinary. In a single second, the temperature fell by billions of degrees. In a single second, the energy density fell significantly. In a single second, the expansion of the universe added enormous volumes of space. Each second of the early universe contained more change, more transition, more evolution than the following millions of years. The first 3 minutes of the universe's existence were more eventful per unit of time than the entire subsequent 13.8 billion years. And yet the mind can follow it, not in the detailed equations. Those require training and tools that most people do not have, but in the broad outline, in the sequence of events, in the way one thing followed from another with a logic that, once you understand it, seems almost inevitable. The temperature fell. At 10 billion degrees, the rate of weak interactions, the interactions that converted protons into neutrons and back, began to drop significantly. The neutrinos had decoupled. The proton-neutron interconversions were slowing. At about 3 billion degrees, reached at around 10 seconds after the Big Bang, the neutron decay had been proceeding for about 9 seconds. The half-life of the free neutron is around 10 minutes, so in 9 seconds, not many neutrons had decayed. The ratio was shifting only gradually, but the temperature continued to fall. 1 billion degrees was the key threshold, the temperature at which deuterium could survive. It took about 100 seconds to reach 1 billion degrees. 100 seconds, less than 2 minutes. In those 100 seconds, several things had happened. The last of the matter-antimatter annihilation had occurred. The electrons and positrons had mostly annihilated each other, leaving just enough electrons, one per proton, to maintain electrical neutrality. The energy released in that annihilation had been transferred to the photons, slightly raising the photon temperature relative to the neutrino temperature. The neutrinos, which had decoupled earlier, did not receive this energy injection. So after electron-positron annihilation, there were two different temperatures in the universe, a slightly higher photon temperature and a slightly lower neutrino temperature. This difference, the neutrino temperature being about 71% of the photon temperature, persists to this day. The cosmic neutrino background, which fills the universe just as the cosmic microwave background does, but is much harder to detect, is at a temperature of about 1.95 degrees Kelvin today, compared to the 2.73 degrees Kelvin of the photon background. We have not directly detected the cosmic neutrino background. Neutrinos interact so weakly with matter that detecting the low-energy neutrinos of the cosmic background is beyond our current technology. But we know it is there. We know its temperature. We know its properties. Because the physics that produces it is well understood and well tested. At 100 seconds, with the temperature at 1 billion degrees, the deuterium bottleneck finally broke. Suddenly, deuterium could form and survive, and when deuterium could form and survive, the nucleosynthesis began. Not gradually, not slowly. The formation of heavier nuclei, once deuterium became stable, proceeded rapidly. In the hot, dense plasma of the early universe, nuclear reactions occurred at rates that would be extraordinary by any ordinary measure. The universe had 3 minutes to make its nuclei, and it did not waste them. Deuterium formed. Deuterium captured neutrons to make tritium. Deuterium captured protons to make helium-3. Tritium captured protons to make helium-4. Helium-3 captured neutrons to make helium-4. Helium-4 formed in large quantities, and there was a further possibility. Helium-4 nuclei could combine with each other to make heavier elements. Beryllium-8, for instance. But beryllium-8 is extraordinarily unstable. Its half-life is about 10 to the minus 16 seconds, meaning that in less time than light takes to cross an atom, it falls apart. The beryllium bottleneck. To make anything heavier than helium-4 in the Big Bang required combining 3 helium-4 nuclei simultaneously, which at the densities and temperatures of the early universe was vanishingly unlikely. There was also the possibility of making lithium-7. A small amount of lithium-7 was made during Big Bang nucleosynthesis by combining helium-4 with helium-3 or through other reactions. The predicted amount of primordial lithium-7 is small, about 1 lithium atom for every 10 billion hydrogen atoms, but measurable in principle. And this is where an interesting tension exists. The observed amount of lithium in the oldest, most primitive stars, the so-called metal-poor halo stars that have the most pristine composition, least contaminated by later stellar processing, is about 3 times lower than the amount predicted by Big Bang nucleosynthesis theory. This is the cosmological lithium problem, and it is a genuine puzzle. The hydrogen and helium predictions match beautifully. The lithium prediction does not match quite as well. Several explanations have been proposed. The lithium in those old stars may have been depleted by stellar physics. Convection in the stellar interior, bringing lithium down to hotter regions where it is destroyed. The stars we are measuring may not be as unprocessed as we assume, or there may be new physics in the nucleosynthesis itself. Some process that depleted lithium during the Big Bang that we are not yet accounting for. The lithium problem is a reminder that even our most successful cosmological models are works in progress. That the agreement between theory and observation, as impressive as it is not perfect. That the universe still has things to teach us even about its most studied early phases. But the hydrogen and helium predictions, the core of Big Bang nucleosynthesis, are in remarkable agreement with observation. And this agreement is what we now go to explore in more depth. Because the first 3 minutes are not just a story of particles and reactions. They are the moment when the universe made its first creative choice, if you can call it that. The moment when the raw quarks and gluons and leptons and photons of the quark epoch resolved into something organized. Something that would persist, something that would carry the story forward, the first nuclei, the first chemistry of the cosmos, and all of it decided, essentially, in the time it would take you to watch a short film. 3 minutes. Less than that, really, for the main action. The universe made its first elements in less time than it takes to boil an egg, and those elements, those first nuclei of hydrogen and helium, are still here, still in the universe, still in you, in some of them, the hydrogen in your cells carrying its origin in the first minutes like a signature, a proof of presence, a record that says, I was there at the beginning. I was there before any star had formed, before any galaxy had condensed, before any planet had cooled enough to have a surface. I was there, and I am still here, in you, tonight. Weinberg's book was published in 1977, and it did something unusual for popular science writing of its era. It did not soften the strangeness of its subject. It did not reassure the reader that the universe was, at some level, familiar and comfortable. It described the early universe exactly as the physics described it, alien, extreme, operating at scales and temperatures completely outside human experience. And it did so with clarity and honesty that made it more, not less, accessible. The title, The First 3 Minutes, was chosen with care. The first 3 minutes was the period Weinberg judged most decisive. The period from the end of the quark epoch through the nucleosynthesis era, when the composition of the universe was determined. Before 3 minutes, the universe was changing too rapidly and at too high a temperature for the stable structures we recognize, atomic nuclei, to form. After 3 minutes, the composition was essentially locked in, and the long, slow process of cooling and structure formation could proceed. 3 minutes. In the life of a universe that is 13.8 billion years old, 3 minutes is a negligible span, less than 100 billionth of the total age of the universe. If you compressed the history of the universe into a single calendar year, the first 3 minutes would correspond to something like the first 100,000th of a second of January 1st. And in those 100,000ths of a second of cosmic time, the universe decided what it would be made of for the rest of its existence. This is worth sitting with for a moment. We tend to think of history as unfolding over long periods. The history of life on Earth spans 4 billion years. Human civilization spans tens of thousands of years. Even the formation of the solar system took tens of millions of years, long timescales, patient processes, change accumulating gradually over geological and biological time. But the history of the universe itself, the history of what the universe is made of, what its fundamental composition is, was decided in 3 minutes. 3 minutes in the first 3 minutes of everything. 3 minutes that established the raw materials from which all subsequent history would be made, and the physics that governed those 3 minutes, the nuclear reactions, the expansion rate, the proton-to-neutron ratio, the temperature thresholds, is the same physics we study in laboratories today. The strong nuclear force that bound protons and neutrons into helium-4 is the same strong nuclear force that operates in particle accelerators and nuclear reactors right now. The weak nuclear force that converted protons and neutrons back and forth is the same weak force responsible for certain types of radioactive decay in the nuclei of atoms being studied right now. The photons that blasted apart deuterium until the universe cooled enough for it to survive are the same photons that illuminate the room you are lying in, just at enormously lower energies. The laws of physics are the same. The conditions were different, unimaginably different. The first few minutes of the universe were unlike anything that has existed since, in terms of temperature and density and the rate at which things were changing. But the rules were the same rules. The physics was the same physics. This is one of the most remarkable things about modern cosmology. We can describe the earliest moments of the universe using the same laws of physics discovered by studying matter at room temperature. Not perfectly, There are regimes near the very beginning where our theories break down, but for the nucleosynthesis era, for the quark epoch, for everything from a microsecond onward, the standard model of particle physics and the general theory of relativity, developed by physicists studying the universe at human scales, apply. They apply, and their predictions are confirmed by observations of the oldest structures in the universe. The universe is, in this sense, parsimonious. It does not have one set of rules for the beginning and another for the present. It has one set of rules, operating at different conditions, producing different outcomes. The extraordinary variety of the present universe, the stars and galaxies and planets and people, is not the product of different physics at different times. It is the product of the same physics at different conditions. And those conditions were set, largely, in the first 3 minutes. Weinberg ends his book with those words about the universe seeming pointless. He was right that the universe does not seem, in the scientific picture, to have a purpose in the sense of an intention. But I think he underestimated how extraordinary it is that it produced anything at all. That the same laws of physics that at 10 to the 32 degrees give you a featureless symmetrical plasma also give you, at the conditions of the first 3 minutes, helium and hydrogen, and at the conditions of stellar cores, carbon and oxygen, and at the conditions of planetary surfaces, water and organic molecules, and at the conditions of biological cells, life, and at the conditions of neural tissue, minds, that can wonder about where they came from. That is all the same physics, applied at different scales, producing different outcomes at each stage, including at the far end of the sequence, the stage where the physics became aware of itself, which is, if anything, more remarkable than any purpose could be. Between 1 minute and 10 minutes after the Big Bang, something happened that has not been repeated anywhere in the universe in any significant way since. The universe made its first elements from scratch, from protons and neutrons, from the raw materials left over after the quark epoch and the matter-antimatter annihilation. In 10 minutes of nucleosynthesis, driven purely by the temperature and density of the expanding plasma, the universe established the chemical composition that would characterize all the ordinary matter in the cosmos for the next 380 million years. And, in its broad outlines, that still describes the cosmic average composition today: 75% hydrogen, 25% helium, trace amounts of deuterium, helium-3 and lithium-7. That is what Big Bang nucleosynthesis produced. That is what it had to produce, given the physics involved. And that is what we observe in the oldest, most primitive regions of the universe. The places least affected by later stellar processing, where the primordial composition is most nearly preserved. The calculation of these abundances is one of the triumphs of modern physics, starting from the known laws of nuclear physics, from the measured properties of the neutron and proton, from the measured coupling constants of the strong and weak forces, from the measured number of neutrino generations, and from the initial conditions of the Big Bang. A single free parameter, essentially the ratio of baryons to photons. The theory predicts the primordial abundances with remarkable precision, and the predictions match. Not perfectly. The lithium problem, as mentioned, represents a real tension. But the hydrogen and helium abundances match to within a few percent. The deuterium abundance, the fraction of primordial deuterium that survived, not destroyed into helium, matches the observations in the most pristine intergalactic gas clouds. The helium-3 abundance, though harder to measure, is consistent. This is extraordinary. We are predicting the outcome of nuclear reactions that occurred 13.8 billion years ago, in conditions of temperature and density that we can only access indirectly from a set of physical laws discovered over the past century. And the prediction matches what we observe in the universe today. Big Bang nucleosynthesis is, in a real sense, one of the best tests of our cosmological model. Better in some ways than the cosmic microwave background because it probes an earlier epoch. It tells us not just that something happened 13.8 billion years ago, but specifically what the temperature and density were at 1 minute after the Big Bang, and what the proton-to-neutron ratio was, and how many neutrino types were present. Let me walk through the nucleosynthesis in some detail, because the sequence of events is interesting and the physics is clean. At 100 seconds, just under 2 minutes, the deuterium bottleneck opened. The temperature had fallen to 1 billion degrees. Photons energetic enough to blast apart deuterium nuclei were now relatively rare. Deuterium began to form and persist. Deuterium is a nucleus consisting of 1 proton and 1 neutron. Its binding energy is 2.2 MeV, modest compared to heavier nuclei, but sufficient to hold it together at 1 billion degrees. Once deuterium was stable, the neutrons that had been floating free in the plasma, slowly decaying, patiently waiting for the temperature to fall, were rapidly consumed in the formation of deuterium. But deuterium was only the first step. The reactions continued almost immediately. 2 deuterium nuclei could fuse to form helium-3 and a neutron, or tritium and a proton. Deuterium plus a proton gave helium-3. Deuterium plus a neutron gave tritium. Tritium plus a proton gave helium-4. Helium-3 plus a neutron gave helium-4. All of these reactions were occurring simultaneously in the plasma of the early universe, and the end product that all of them were feeding into, the ultimate sink, was helium-4. Helium-4 is an extraordinarily stable nucleus. 2 protons and 2 neutrons arranged in a tight, symmetric configuration that maximizes the strong nuclear force binding. The binding energy per nucleon in helium-4 is about 7 MeV, much higher than deuterium's 2.2 MeV, much higher than tritium's, much higher than helium-3's. Once helium-4 formed, it was very difficult to destroy it under the conditions of the early universe. The photons available were not energetic enough to break it apart. The temperature was falling too fast for the universe to develop the conditions to go further. So helium-4 accumulated. Every available neutron ended up in a helium-4 nucleus. The nucleosynthesis was, in this sense, highly efficient. Virtually all the neutrons that existed at the start of nucleosynthesis ended up locked inside helium-4. Now let's do the arithmetic again, slightly more carefully. At the start of nucleosynthesis, at roughly 100 seconds, the proton-to-neutron ratio was approximately 7:1. Let us work with 14 protons and 2 neutrons as our sample group, maintaining the ratio. Each helium-4 nucleus requires 2 protons and 2 neutrons. With 2 neutrons available, we can make 1 helium-4 nucleus using 2 protons and 2 neutrons. The remaining 12 protons stay as hydrogen nuclei, lone protons, the simplest possible nucleus. Mass account: the helium-4 nucleus has mass 4 units. The 12 hydrogen nuclei have mass 12 units. Total mass: 16 units. Helium mass fraction: 4 out of 16, which is 25%. Hydrogen mass fraction: 12 out of 16, which is 75%. The numbers are so clean they almost look contrived, but they are not. They follow inevitably from the 7:1 proton-to-neutron ratio, which follows inevitably from the physics of the first second, which follows inevitably from the properties of the neutron and proton, the strength of the weak nuclear force, and the expansion rate of the early universe. Everything is connected. Every part of the calculation feeds into every other part. The ratio is what it is because the neutron mass is what it is. The neutron mass is what it is because of the masses of the quarks that compose it. The quark masses are what they are because of their interactions with the Higgs field. The Higgs field is what it is because of the symmetry breaking in the electroweak transition, and the electroweak transition that occurred at the temperature it did because of the structure of the standard model. The composition of the universe, 75% hydrogen, 25% helium, is a consequence of particle physics, of the specific properties of the fundamental particles and forces, of the way the standard model is put together. If any of these parameters had been significantly different, if the neutron-proton mass difference had been different, if the weak force coupling constant had been different, if there had been 4 neutrino generations instead of 3, the composition would have been different, and different compositions would produce different stars, different stellar processes, different elemental abundances, a different universe. The universe we have is the universe that arises from the specific set of physical parameters that happen to be true. This is a statement so obvious it seems trivial, but it has profound implications. The fact that the parameters allow a universe with stable atoms, long-lived stars, carbon chemistry, and complex structure, this is something that required, among other things, the specific composition produced by Big Bang nucleosynthesis. Whether this reflects something deeper, a multiverse selecting for habitable conditions, some as yet unknown principle that constrains the parameters, or simply the unremarkable fact that in a universe with these parameters, observers arise and notice they exist, is a question that remains open. It is beyond the scope of tonight's story, but it is worth knowing that the question exists. The nucleosynthesis itself lasted in its most active phase from about 2 minutes to about 10 minutes after the Big Bang. By 10 minutes, the temperature had fallen to about 100 million degrees. Still extremely hot by any ordinary measure, but cool enough that the nuclear reaction rates had become negligible. The nuclei that had formed were now stable. The composition of the universe was locked in. 10 minutes. 10 minutes in which the universe decided what it would be made of for the next 30.8 billion years. Let me dwell on this for a moment, because I think it deserves more than a passing acknowledgement. At 10 minutes after the Big Bang, the universe was already done with the most consequential chemistry it would ever perform. Everything that came later, the formation of stars, the fusion of heavier elements in stellar cores, the dispersal of those elements in supernovae, the formation of planets and the emergence of life, and the development of minds capable of curiosity, all of it is downstream of what happened in these 10 minutes. The substrate, the raw material, the starting ingredients were set in the first 10 minutes. You find 75% hydrogen, 25% helium, trace of deuterium, trace of helium-3, tiny amount of lithium-7. That is what the universe had to work with, and it did extraordinary things with it. Stars formed from clouds of this primordial gas, mostly hydrogen, with a quarter helium. Inside those stars, hydrogen fused to helium. In the larger stars, helium fused to carbon, carbon to oxygen, oxygen to neon, neon to magnesium, magnesium to silicon, silicon to sulfur, and through a cascade of fusion reactions all the way up to iron. In the most violent events, supernovae and neutron star mergers, elements heavier than iron formed. Gold, uranium, iodine, barium, all forged in the extreme environments of dying stars. And the hydrogen at the beginning of all of this. The hydrogen that stars burned as fuel, that fueled the nuclear reactions that created every element heavier than lithium. That hydrogen was made in the first 10 minutes. The oxygen in your blood was made in the core of a star. The carbon in your cells was made in the core of a star. The iron in your hemoglobin was made in a supernova. But the hydrogen in the water in your cells, the hydrogen bonded to all those heavier atoms, the hydrogen that is part of every organic molecule in your body, that hydrogen is primordial, made in the first 10 minutes. As old as the universe itself, right now, the hydrogen in your body carries a signature of the first minutes of the universe. It carries the proton to neutron ratio of 1 second after the Big Bang in its very existence. The fact that it exists as hydrogen, as a lone proton, is because there were too many protons and too few neutrons for all of them to be incorporated into helium. The surplus protons, the 7-to-1 surplus, remained as hydrogen. And those surplus protons, those primordial hydrogen nuclei, made their way into the water in your cells and the organic chemistry of your life. You are carrying the arithmetic of the first second in your body chemistry, which is strange and somehow settling and true. There is one more thing to say about Big Bang nucleosynthesis before we leave it. Something about the way it relates to our confidence in the whole picture. We cannot directly observe the Big Bang. We cannot observe the quark-gluon plasma. We cannot observe the matter-antimatter annihilation. These events occurred 13.8 billion years ago, in conditions that no instrument we will ever build can recreate at cosmic scale. We know about them through their consequences, through the properties of the universe as we observe it today. Big Bang nucleosynthesis is one of our clearest windows into the early universe, because its products are still observable. The primordial abundances of hydrogen, helium, deuterium, helium-3 and lithium are preserved in the oldest, least processed structures in the universe. Astronomers can measure these abundances in old stellar spectra, in intergalactic gas clouds, in the spectral signatures of distant quasars. And when they do, they find numbers that match the predictions of the Big Bang model. This is what it means to say that a scientific theory is confirmed. Not that we were present at the event, not that we have perfect, exhaustive knowledge of every detail, but that the predictions the theory makes about observable things, things we can actually measure today, match the observations. The theory passes the test again and again, in independent measurements by different scientists using different instruments and different techniques. The Big Bang is not a belief, it is a description of the universe that has been tested in multiple ways and found to be correct. The nucleosynthesis is one of those tests, and it passes. At 10 minutes after the Big Bang, the nucleosynthesis was essentially over. The universe had its elements, not all the elements, just the lightest ones. Just hydrogen and helium and traces of a few others. The heavier elements, the carbon and oxygen and iron and gold and everything else on the periodic table beyond lithium, those would come later in the cores of stars. But the raw material was in place, and the universe, now 10 minutes old, was moving into its next long phase. Not a phase of rapid change, not a phase of extraordinary events. A long, slow, patient phase of cooling and expanding and waiting. The next major transition was not 10 minutes away. It was not 100 minutes away. It was 380,000 years away. The universe, after its extraordinary first 10 minutes, was about to enter a long, quiet era. The fog was settling in. There is one more dimension of Big Bang nucleosynthesis that deserves attention before we leave it. The precision of the measurement. When cosmologists speak of the primordial helium abundance being about 25%, they are not giving a rough estimate. The modern measurements of the primordial helium mass fraction are precise to a few tenths of a percent. Measurements of metal-poor HII regions, ionized gas clouds in nearby dwarf galaxies, where stellar processing has been minimal, give primordial helium mass fractions of around 0.245 to 0.250. The theoretical prediction from Big Bang nucleosynthesis, using the baryon density determined from the cosmic microwave background, is about 0.247. That is agreement to within the measurement uncertainties. The deuterium measurement is similarly precise. Observations of pristine intergalactic gas clouds along quasar sightlines give primordial deuterium to hydrogen ratios consistent with the theoretical prediction to within a few percent. What this means is not just that the Big Bang happened. It means that the specific physics of the first 10 minutes, the specific proton to neutron ratio, the specific expansion rate, the specific nuclear reaction rates, were what the theory says they were. We can read the universe's first 10 minutes in the composition of its oldest, least processed material, and the reading is consistent with the calculation. Now, this is, to my mind, one of the most remarkable achievements in the history of science. Not because it is the most complex calculation, not because it requires the most sophisticated equipment, but because it connects, quantitatively and precisely, the physics of a laboratory, the strong force coupling constant, the neutron-proton mass difference, the weak force coupling, to the composition of material 13.8 billion years old. The universe, at 10 minutes of age, performed a nuclear physics calculation. We can reproduce that calculation on paper or on a computer using physics developed in the 20th century, and the answers match. The universe's first chemistry and our best physics are in agreement, which means that the story we have been telling tonight is not guesswork. It is not mythology or metaphor. It is science, specifically, quantitatively, testably correct science. The quark-gluon plasma, the matter-antimatter asymmetry, the nucleosynthesis, all of it has left fingerprints in the universe that we can still read today. The composition of the universe was written in the first 10 minutes, and it is still there, in the oldest stars, waiting to be read. At 10 minutes after the Big Bang, the universe was a different place from what it had been at the beginning, but it was still a place that nothing we know would have recognized. The temperature was about 100 million degrees Kelvin. That is still hot enough to be described as extreme by any ordinary standard, hot enough to vaporize anything material, hot enough to strip electrons from atoms, hot enough to keep the universe in a state of plasma. But it was vastly cooler than it had been at the first second, or the first microsecond, or the first fraction of a millisecond. The universe had cooled by a factor of roughly 100 billion from its peak temperature. What existed at 10 minutes? Photons. Vast numbers of photons streaming in every direction, interacting with the charged particles of the plasma, carrying the energy that dominated the universe's total energy budget. Protons, the surviving remnant of the matter-antimatter annihilation, the 1 in a billion excess. In enormous absolute numbers, there are roughly 10 to the 80 protons in the observable universe, but constituting only a small fraction of the universe's total energy. Helium-4 nuclei, making up about 25% of the matter by mass. Tightly bound, stable, already locked into their permanent form. Electrons, 1 per proton, maintaining electrical neutrality, moving through the plasma, scattering off photons, carrying charge through the hot gas. Neutrinos, decoupled from the rest of the matter, streaming freely through the universe, essentially invisible to the other components, filling all of space, carrying a temperature of about 1.4 times 10 to the 9 degrees Kelvin. At this point, falling toward the 1.95 degrees Kelvin they will reach in the present-day universe. Trace amounts of deuterium, helium-3 and lithium-7. Small remnants of the nucleosynthesis that did not go all the way to helium-4, constituting a tiny fraction of the matter, but measurable in principle and actually measured in the present universe. No atoms, no neutral atoms, anyway. The plasma was still hot enough that any electron that bound to a nucleus, attempting to form a proper atom, would immediately be knocked free again by a photon. The photons were still energetic enough to ionize hydrogen and helium, so the electrons and nuclei existed separately, and the universe was a fully ionized plasma. And a fully ionized plasma is opaque to light. This is a crucial point. In the early universe, photons could not travel freely. They were constantly interacting with the charged particles, being scattered by electrons, absorbed and re-emitted, zigzagging through the plasma in a random walk that severely limited how far they could go. The universe was opaque, foggy, dense with interacting particles and radiation. Light could not travel through it, which means we cannot see it. The cosmic microwave background, the oldest light we can observe, is not from the nucleosynthesis era. It is from much later, when the universe had cooled enough for atoms to form and the fog to clear. The nucleosynthesis era, the quark epoch, the inflationary period, all of this is hidden from direct observation behind the fog of the hot early plasma. This is not a failure of our instruments. It is a fundamental limit set by the physics of the early universe. Before about 380,000 years, the universe was opaque to electromagnetic radiation. We cannot see through it any more than we can see through a wall of fog. Our telescopes, however powerful, can never directly image the Big Bang or the nucleosynthesis era. We know about those times through other means. Through the neutrino background, which decoupled earlier, and in principle preserves information about that era, though we cannot yet detect it directly at cosmological energies. Through gravitational waves which interact so weakly that they travel freely through even the densest plasma and could carry information from the very earliest moments. Though detecting primordial gravitational waves is an extraordinary technical challenge that is just beginning to be approached, and through the residue we have been describing. The composition of the universe, the primordial abundances of the light elements, these are like forensic evidence, not a direct observation of the event, but the preserved consequences of the event from which the event can be reconstructed. At 10 minutes, the universe was opaque and hot and expanding. What happened next was simpler than what had come before. No dramatic phase transitions, no extraordinary particle physics, just expansion, just cooling. The universe, like a very large gas expanding into a very large volume, getting cooler and less dense with every passing moment. For about 50,000 years, the universe was radiation-dominated. The energy of radiation, photons and neutrinos, exceeded the energy of matter. During this period, the expansion of the universe was governed by the physics of radiation. At around 50,000 years, the energy density of matter became comparable to the energy density of radiation. The universe became matter-dominated. This transition changed the dynamics of the expansion and the way that small perturbations, the tiny overdensities left by the quantum fluctuations of inflation, would grow over time. In a matter-dominated universe, gravity has more time to pull overdense regions together, allowing structures to grow. But there was still a problem. The matter, the protons and helium nuclei and electrons, was still coupled to the radiation through electromagnetic interactions. Electrons scattered photons constantly. Every time gravity tried to pull matter together in an overdense region, the radiation pressure pushed it back out. The matter and radiation were locked together in a kind of acoustic oscillation, a compression followed by expansion, followed by compression, like a sound wave, but operating on cosmic scales with matter and light as the medium. These oscillations, the cosmic acoustic oscillations, left their signature in the cosmic microwave background. They are visible in the precise pattern of temperature fluctuations in the CMB as observed by satellites like WMAP and Planck. The peaks and troughs in the angular power spectrum of the CMB temperature fluctuations are the frozen signature of these acoustic oscillations at the moment of recombination, when the universe finally became transparent. Because at about 380,000 years after the Big Bang, the universe crossed another critical threshold. The temperature had fallen to about 3,000 degrees Kelvin. At this temperature, a proton can capture an electron and hold on to it. The electron has enough energy to remain bound to the proton, to form a proper hydrogen atom rather than being knocked free by a passing photon. The photons, at 3,000 Kelvin, are no longer energetic enough to ionize hydrogen. This transition, from a plasma of free electrons and nuclei to a gas of neutral atoms, is called recombination. The name is slightly misleading, since the electrons and nuclei had never actually combined before in the history of the universe. It would be more accurate to call but recombination is the established term. and we are stuck with it. At recombination, the universe changed from opaque to transparent. When the electrons bound to nuclei and became neutral atoms, the main target for photon scattering disappeared. Photons no longer had free electrons to scatter off. They could travel freely. For the first time in the universe's 380,000-year history, light could move unimpeded through space. The photons that were released at this moment, the photons that were traveling freely through the universe when recombination occurred, have been traveling ever since. For 13.8 billion years, in every direction, filling all of space. Getting colder as the universe expands, their wavelengths stretching as space stretches, their energies decreasing as they redshift. We can detect those photons today. They are the cosmic microwave background, the faint glow that fills the sky in every direction in microwaves at a temperature of about 2.73 degrees Kelvin, barely above absolute zero, the oldest light in the universe, the afterglow of the Big Bang. When you look at the cosmic microwave background, you are seeing the surface of last scattering, the moment when the universe became transparent. You are looking at photons that have been traveling since 380,000 years after the Big Bang. You are looking, in a very real sense, at the edge of the observable universe in time, the farthest back we can see with light. The CMB carries extraordinary information. Its temperature variations, the tiny fluctuations of about 1 part in 100,000, are the imprint of the quantum fluctuations from inflation processed through 380,000 years of plasma oscillations. By analyzing the pattern of these fluctuations, cosmologists can extract a wealth of information about the early universe, the composition of the universe, the geometry of space, the expansion rate, the amplitude of primordial fluctuations, and more. The CMB is, in a sense, the Rosetta Stone of cosmology. It encodes the history of the universe from the first fraction of a second through to 380,000 years, in a pattern of temperature fluctuations that we can map and analyze. The satellites that have measured the CMB, COBE, WMAP, Planck, have produced some of the most scientifically productive measurements in the history of astronomy. And the CMB is still out there. Right now, as you lie in the dark, photons of the cosmic microwave background are passing through this room, through the walls, through you, billions of photons per second, per square meter, all the time, from every direction, carrying their ancient message from the edge of the observable universe in time. They do not interact with you. They pass through as if you were not there, because at their low energy, the interaction cross-section with ordinary matter is negligible. But they are there, the oldest light in the universe, passing through you in the dark right now. After recombination, the universe entered what cosmologists call the cosmic dark ages. Not dark in the metaphorical sense of difficult or distressing, dark in the literal sense. After recombination, the universe contained neutral hydrogen and helium gas, but no stars, no sources of light, no galaxies, just gas, expanding, cooling, slowly becoming clumped under the influence of gravity at the locations seeded by the primordial fluctuations. The universe was, in this period, genuinely dark. Not the darkness of a night sky, which contains stars and the faint glow of the Milky Way and the reflections of city lights. The darkness of a universe before any star had formed. Absolute darkness, except for the cosmic microwave background, now fading into infrared and then microwave as the universe expanded. The Dark Ages lasted from about 380,000 years to somewhere between 150 million and 800 million years after the Big Bang. The uncertainty in the end date reflects the fact that the first stars may have formed at different times in different places, and the transition from dark to light was not a single moment but a gradual process. During the Dark Ages, the gas was slowly, steadily, patiently falling together under gravity. The small overdensities from inflation and recombination, regions where the density was just fractionally higher than average, were growing. Gravity pulled more gas into those overdense regions. The overdensities became more overdense. Dark matter, the mysterious invisible component of the universe that makes up roughly 27% of its energy budget, was also clumping, forming the gravitational scaffolding on which ordinary matter would later congregate. And slowly, across millions of years, the gas fell into deeper and deeper gravitational potential wells. It heated as it fell, compressed by gravity. It formed filaments and sheets and voids. The cosmic web, a vast three-dimensional structure of matter organized by the gravity of both ordinary and dark matter. And at the densest nodes of this web, where gas had fallen deepest and compressed most, something extraordinary was building. The first stars. Not yet, not quite yet in our story, but the dark ages were ending. The gas was compressing, the temperature was rising in the densest regions, and at a certain point, at a critical density and temperature, the physics of nuclear fusion would become relevant again. Not the nucleosynthesis of the Big Bang, which had been driven by the extreme temperatures and densities of the early universe and had locked in the primordial abundances. Something new, something driven by the gravity of collapsed gas clouds, something that would produce light for the first time in hundreds of millions of years, in a universe that had been dark since recombination. The first stars were coming, and with them, the first starlight, the end of the Dark Ages. The beginning of the universe we more nearly recognize. The hydrogen from the first 10 minutes was about to start burning, and in that burning, it would make everything else. There is something worth knowing about the cosmic microwave background that goes beyond its role as an afterglow or a snapshot. It is a message, not an intentional message, not sent by anyone, but a record encoded in the precise pattern of its temperature fluctuations, of everything that happened in the universe, from the quantum fluctuations of inflation through the plasma physics of the first 380,000 years. The message is there in every direction, in the faint microwave glow that fills the sky. And cosmologists have spent decades developing the mathematical tools to read it. The angular power spectrum of the CMB, a plot showing the amplitude of temperature fluctuations at different angular scales on the sky, has a specific shape, a series of peaks and troughs, each encoding different information. The position of the first peak tells us the geometry of space. The relative heights of successive peaks tell us the ratio of baryonic matter to dark matter. The overall amplitude tells us the amplitude of the primordial fluctuations from inflation. The slight asymmetry between even and odd peaks tells us about the baryon density in the early universe. By analyzing the CMB with satellites, COBE in the 1990s, WMAP in the 2000s, Planck in the 2010s, cosmologists have constructed what is now called the Standard Cosmological Model, or lambda CDM. Lambda for the cosmological constant representing dark energy, CDM for cold dark matter. This model describes the composition and history of the universe with remarkable precision. According to this model, the universe is approximately 5% ordinary baryonic matter, the quarks and electrons and atoms we have been describing all night, about 27% dark matter, an invisible, non-baryonic substance whose gravitational effects are clearly detected, but whose nature remains unknown, and approximately 68% dark energy, a mysterious component, possibly the energy of empty space itself, that is causing the expansion of the universe to accelerate. 5%. Everything we can see, touch, and are made of is 5% of the total energy budget of the universe. The protons and neutrons from the quark epoch, the hydrogen and helium from nucleosynthesis, the stars and galaxies and planets and people. 5%. The other 95% is, in a precise and literal sense, unknown. Dark matter has been detected through its gravitational effects. It bends light, it holds galaxies together, it organizes the large-scale structure of the universe. But we do not know what it is. It is not made of atoms. It does not emit or absorb light. It interacts gravitationally and possibly weakly, but not electromagnetically. Decades of searches for dark matter particles in underground detectors, in particle accelerators, in astrophysical observations have so far not conclusively identified the specific particle or field that dark matter consists of. Dark energy is even more mysterious. It is the dominant component of the universe's energy budget, driving the accelerating expansion that was discovered in 1998 when astronomers observed that distant supernovae were fainter than expected, meaning the universe had been expanding faster in the recent past than in the distant past, meaning the expansion was speeding up rather than slowing down. This was a shock. It was expected, based on the matter in the universe, that gravity would be slowing the expansion. Instead, it was accelerating. Dark energy is what is causing this acceleration. It is consistent with Einstein's cosmological constant, an energy density inherent to empty space, constant in density as space expands. But why empty space should have this particular energy density? Small enough that it did not dominate the universe during the matter-dominated era of structure formation, large enough to dominate now, is one of the deepest puzzles in physics. So the universe we have been described tonight, the one that emerged from the Big Bang, cooled, made hydrogen and helium, produced stars, distributed elements, produced the solar system and the Earth, and you is the 5% minority of the total. The universe you can see and touch and are made of is the small fraction. The majority is invisible and unknown. This might seem diminishing, like finding out that the ocean you thought you were swimming in is actually a puddle compared to the vast invisible ocean surrounding it. But I find it has the opposite effect if you let it. It means the universe is larger and stranger and more various than we know. It means the story we've been telling tonight, as extraordinary as it is only part of the story. The visible universe, the baryonic universe, the 5%, that is what we can see. The rest is there, participating in everything through gravity, organizing the structure of the cosmos in ways we can detect but not yet fully explain. The Dark Ages were dominated by the unseen majority. Dark matter halos forming first, baryonic gas falling in later. The visible universe organized by the invisible one. And the CMB, the afterglow of recombination, the moment when the 5% barrier beyonds became neutral and transparent, is the light that was released when the fog of the early plasma cleared. It carries the imprint of both the baryonic physics and the dark matter gravitational effects. It is a window into the full composition of the universe at 380,000 years. Right now, as you lie in the dark, that ancient light is passing through this room. Billions of photons per second per square meter from every direction at 2.73 Kelvin. Too cold to see, too cold to feel, but real, physically present, in this room, in the air, passing through your body without interaction. The universe's oldest light, the afterglow of the moment the fog cleared, still travelling after 13.8 billion years. And in the dark ages that followed that clearing, in the 200 million years of quiet gravitational work, the universe was building up to its next great act. The first stars were forming. The hydrogen from the first 10 minutes was about to start burning, and the universe was about to become a much more interesting place. 200 million years. That is roughly how long the universe sat in the dark after recombination, after the plasma cleared and the cosmic microwave background streamed free and the fog lifted, and the photons of the early universe finally had room to travel. After all of that, after the extraordinary first 10 minutes, and the long cooling and the acoustic oscillations, and the moment of recombination, The universe was dark for 200 million years. We tend to think of darkness as an absence of light, of warmth, of activity, the darkness of a closed room, the darkness of a winter night, the darkness behind closed eyes. But the dark ages of the universe were not an absence of activity. They were a period of slow, patient, enormous gravitational work. A period when the universe was doing something it had never had time to do before, building structure. From the very first moments, the universe had been changing too rapidly for structure to develop. In the quark epoch, at a microsecond, there were no stable structures larger than a proton. In the nucleosynthesis era, at a few minutes, there were nuclei but no atoms. At recombination, at 380,000 years, there were neutral atoms but no molecules, no planets, no stars, just gas. An enormous, expanding, cooling, slowly darkening cloud of hydrogen and helium with trace amounts of lithium stretching across every direction. But it was not perfectly uniform gas. The quantum fluctuations from the inflationary era, those tiny, random variations in energy density that inflation had stretched from microscopic to cosmic scales, had left their imprint in the distribution of matter. Some regions were just fractionally denser than average, 1 part in 100,000. Not much, but gravity works with what it has, and it is patient. In an overdense region, there is slightly more gravitational pull. That pull attracts slightly more matter from the surrounding regions. As more matter falls in, the gravity increases. As the gravity increases, the infall accelerates. Slowly, over millions and then hundreds of millions of years, the overdense regions grew denser still, while the underdense regions became emptier. This is gravitational instability, the process by which the tiny inhomogeneities of the early universe become the large-scale structure of the late universe. The cosmic web, the vast network of filaments and sheets and clusters and voids that organizes the matter of the observable universe into its current architecture. Dark matter played a crucial role in this process. Dark matter, the invisible non-baryonic component that constitutes roughly 27% of the universe's total energy budget, was present throughout the Dark Ages, clumping under its own gravity even before ordinary matter could. Because dark matter does not interact with photons electromagnetically, it was not held up by radiation pressure during the plasma era. While ordinary matter was being pushed around by the acoustic oscillations, the compression and rarefaction waves driven by the interplay of gravity and radiation pressure, dark matter was free to begin clumping earlier. By the time of recombination, dark matter had already formed the gravitational wells, the halos, into which ordinary matter would later fall. The seeds of galaxies were dark matter halos. The gas of hydrogen and helium, freed from the radiation pressure at recombination, began falling into those halos, and as it fell, it compressed, and as it compressed, it heated. And at the densest centers of the largest collapsing gas clouds, the temperature and density rose toward the conditions for nuclear fusion. The Dark Ages were not empty. They were full of invisible gravitational work, full of dark matter organizing itself, full of gas slowly falling, full of the patient accumulation of the conditions for light. And then, somewhere between 150 million and 400 million years after the Big Bang, the exact timing is uncertain and likely varied from place to place, the first stars ignited. We call them population 3 stars. The name places them in a sequence. The Sun and stars like it are population I, old stars in the galactic halo are population 2, and the first stars, the oldest, most primitive, most chemically pristine, are population 3. This classification was developed before any population 3 stars were directly observed, purely on theoretical grounds, to distinguish stars of different chemical compositions. Population 3 stars were made of the only materials that existed, hydrogen and helium from Big Bang nucleosynthesis, with a trace of lithium, no carbon, no oxygen, no iron. No metals in the astronomical sense, just the primordial gas with its 75-25 composition falling under gravity into a protostellar core. The absence of metals had a profound effect on the properties of these first stars. In modern stellar astrophysics, the metals, carbon, oxygen, and other heavy elements, are important for how a star radiates energy. They contribute to the opacity of stellar gas, meaning they affect how readily the gas absorbs and re-emits radiation. In a metal-rich gas, radiation from the stellar interior is efficiently absorbed by the gas and re-emitted, creating a pressure that supports the star against gravity. In a metal-free gas, the opacity is much lower. Radiation passes through more easily. The implication is significant. A metal-free gas cloud collapsing into a star cannot fragment as easily as a metal-rich cloud. Modern star formation typically involves a collapsing cloud fragmenting into many smaller pieces, producing a cluster of stars with a range of masses, some small, some large, most like the Sun or smaller. A metal-free cloud with lower opacity and therefore less effective radiative cooling tends to produce fewer, more massive fragments. The theoretical prediction is that population 3 stars were, on average, much more massive than modern stars. Estimates from numerical simulations suggest typical masses of hundreds of solar masses. Some models predict stars of 500 or even 1,000 solar masses. These would be objects far larger than anything that forms in today's galaxy. Cosmic giants compared to the Sun, burning with a ferocious luminosity and living very short lives. A massive star burns through its fuel fast. A star of 100 solar masses might live only a few million years before exhausting its hydrogen. A star of 500 solar masses might live less than that. Compared to the 10 billion year lifespan of the Sun, these first stars were brief in cosmic terms, brilliant and brief, like candles that burn at both ends simultaneously. But in those few million years, their cores were furnaces. Nuclear fusion in a stellar core begins with hydrogen burning, the fusion of hydrogen nuclei into helium. This is the same process in broad principle that occurs in the Sun. But in a massive star, the core temperature is much higher, the pressure much greater, and the rate of fusion enormously faster. The Sun converts about 600 million tons of hydrogen into helium every second. A star of several hundred solar masses would be converting hydrogen at a rate millions of times higher. When the hydrogen in the core was exhausted, helium burning began. 3 helium-4 nuclei combining in the triple alpha process to form carbon-12. Then carbon burning, oxygen burning, neon burning, magnesium burning, silicon burning. A cascade of thermonuclear reactions, each occurring at progressively higher temperatures in the ever-contracting, ever-hotter core. Each step fusing the ashes of the previous step into something heavier, carbon to oxygen, oxygen to neon, neon to magnesium, magnesium to silicon, silicon to sulfur, and eventually at the end of the chain, to iron. Iron is the end of the road for fusion in stellar cores. The iron nucleus, 26 protons and 30 neutrons, is the most tightly bound nucleus in nature. Fusing iron nuclei into heavier elements does not release energy, it requires energy. So when an iron core develops at the center of a massive star, the energy source stops. Fusion stops. The core, which had been held up against gravity by the outward pressure of nuclear energy release, suddenly has no source of pressure, and gravity, which does not negotiate, takes over. The iron core collapses. In less than a second, in about a quarter of a second, the iron core, which has the mass of 1 or 2 suns, collapses from a size comparable to the Earth to a sphere about 10 kilometers across. The density reaches that of an atomic nucleus, and then higher. The neutrons and protons in the core are squeezed together so tightly that the quantum mechanical pressure of neutrons, the Pauli exclusion principle, which does not allow 2 identical fermions to occupy the same quantum state, finally halts the collapse. The core bounces. and the shock wave from that bounce propagates outward through the infalling outer layers of the star. It is, in the simplest description, one of the most energetic events that occurs in the present universe. In the seconds of a core collapse supernova, more energy is released than the Sun will release in its entire 10 billion year lifetime, mostly as neutrinos which carry away the binding energy of the neutron star, but a fraction of that energy goes into the explosion. The blast wave that tears the outer layers of the star apart and flings them into space at thousands of kilometers per second. And in those outer layers, in the extreme temperatures and neutron fluxes of the expanding supernova shock, elements heavier than iron are created. The rapid neutron capture process, the R process, occurs in the supernova environment. Neutrons are captured by nuclei faster than the nuclei can undergo beta decay, building up neutron-rich isotopes and then decaying to produce heavy elements. Gold, platinum, uranium, thorium, barium, strontium, a spray of heavy elements, most of them previously non-existent in the universe, produced in the seconds of the supernova and flung outward into the surrounding gas. We now know that neutron star mergers, the violent collision and coalescence of two neutron stars in a binary system, are also a major, perhaps the dominant, site of our process nucleosynthesis. In 2017, the detection of gravitational waves from a neutron star merger, followed by the observation of the associated electromagnetic counterpart, a kilonova, confirmed that heavy elements, including gold, were being produced in the explosion. The gold in any piece of jewelry you own was almost certainly produced in such a merger, or in a supernova, billions of years before the solar system formed. The first population 3 stars exploded in supernovae or collapsed directly back to black holes. For the most massive, the collapse may have been so rapid and so complete that no bounce occurred, no supernova, just a direct implosion to a black hole. But the ones that did produce supernovae scattered their nucleosynthetic products: carbon, oxygen, silicon, iron, and traces of heavier elements into the surrounding interstellar medium. The next generation of stars, population 2 stars, formed from this enriched gas. Not pristine hydrogen helium anymore. Gas with a small but non-zero metal content. Gas that could cool more efficiently, that could fragment into smaller clumps, that produced stars with a range of masses closer to what we see today. And those population 2 stars went through their own cycles of nucleosynthesis and death, further enriching the interstellar medium. Over billions of years, across multiple generations of stellar birth and death, the heavy element content of the galaxy's gas increased steadily. The interstellar medium became richer in carbon, oxygen, silicon, magnesium, iron, and all the other elements. And somewhere in the Milky Way, about 4.6 billion years ago, a particular cloud of gas collapsed. It was a molecular cloud, a cold, dense region of the interstellar medium where hydrogen had combined into molecular form, where the gas had cooled enough to allow gravity to pull it together. It was enriched with heavy elements from multiple generations of stellar processing. It had, in addition to hydrogen and helium, carbon and oxygen and silicon and iron and sulfur and phosphorus, and all the elements needed for chemistry of extraordinary complexity. That cloud collapsed. At its center, a star ignited, the Sun. Around it, from the material that did not fall into the stellar core, a disk formed. In that disk, dust particles stuck together, growing to pebbles, pebbles to boulders, boulders to planetesimals, planetesimals to planets. The rocky planets, including the third one, formed from this disk over about 100 million years. And on the third planet, in the thin film of water and rock and gas that constitutes its surface layer, something extraordinary happened. The chemistry of carbon, the chemistry of a universe that had been forging and distributing carbon for billions of years, found conditions hospitable to an extraordinary level of complexity. Molecules that could copy themselves. processes that selected for copying fidelity, the slow, patient accumulation of complexity that we call life. And from the first cell to the first multicellular organism, to the first animal, to the first vertebrate, to the first mammal, to the first primate, to the first human. Another long, patient chain of consequence, operating now through evolution rather than stellar physics, but no less continuous, no less connected to the beginning. You are at the far end of two chains of consequence. One cosmological, the Big Bang, to the quark epoch, to nucleosynthesis, to recombination, to the dark ages, to the first stars, to stellar evolution, to the solar nebula, to the Earth. One biological, the first cell to the first complex organism, to the first animal, to the first vertebrate, to the first primate, to you. The two chains meet in your body. The cosmological chain contributed the atoms. The hydrogen from the Big Bang, the carbon and oxygen and iron from stars. The biological chain contributed the arrangement, the specific, intricate, extraordinary organization of those atoms into a living, thinking being. You are the intersection of cosmic history and biological history. You are where the universe's chemical past meets the Earth's evolutionary present. And tonight, in the quiet, both histories are at rest. The first light ended the Dark Ages. The first stars began the chain of stellar chemistry that eventually produced your atoms. And in a universe that was once entirely dark, there is now a room and a person in it, and for a few hours the long journey of matter comes to a temporary resting point. The atoms that were in the fire of the first stars are in you now, and they are still. The first stars did more than make elements. They also created something the universe had not yet had: ionizing radiation. Ultraviolet photons energetic enough to strip electrons from hydrogen atoms. And this radiation, streaming outward from the first stellar populations, began to reionize the neutral hydrogen that had formed at recombination and persisted through the Dark Ages. This process is called reionization, and it marks the end of the cosmic Dark Ages in a second complementary sense. The Dark Ages ended in the first sense, the literal end of darkness, when the first stars ignited and produced light. They ended in the second sense, the end of the universe being filled with neutral, opaque hydrogen when the ultraviolet radiation from those stars reionized the surrounding gas. Reionization was a gradual process. It did not happen all at once. The first stars ionized bubbles of gas around themselves. Those bubbles grew, adjacent bubbles merged. The ionized fraction of the intergalactic medium grew from nearly zero at the end of the Dark Ages to nearly complete by around 1 billion years after the Big Bang. The transition from a neutral universe to a nearly fully ionized one took hundreds of millions of years. The evidence for reionization is encoded in the spectra of distant quasars. Quasars are the extraordinarily luminous centers of galaxies powered by supermassive black holes, and the most distant quasars are among the brightest objects in the observable universe, visible across billions of light years. The light from a distant quasar, as it travels to us, passes through the intergalactic medium. If that medium contains neutral hydrogen, specific wavelengths of the quasar's light are absorbed by the hydrogen. By examining the pattern of absorption in quasar spectra at different redshifts, corresponding to different epochs in cosmic history, astronomers can trace the reionization of the universe over time. The first stars, forged from the primordial hydrogen and helium of the Big Bang nucleosynthesis, not only enriched the universe with heavy elements, they also transformed the state of the intergalactic medium. They ended the era in which the universe was filled with neutral, opaque gas and began the era of the ionized, transparent intergalactic medium that persists today. The universe that exists now, with its transparent intergalactic medium, its complex chemistry of heavy elements, its second and third generation stars like the Sun, is a direct consequence of what those first population 3 stars did. They were brief, they were enormous, They were made of the purest primordial material, and in their short lives and violent deaths, they initiated the chain of stellar and chemical evolution that eventually produced everything that came after, including the atoms in your body, including you. The first light lit up the universe. The first stars began the process that made you possible, and the hydrogen they burned, the hydrogen that powered those first stellar fires, was the hydrogen made in the first 10 minutes. The circle from the first 10 minutes to you is complete. Let me tell you what you are made of, not in the biological sense, not the tissues and organs and cells that constitute your body as it is right now, at this moment. In the deeper sense, the 13.8 billion years sense, the sense that does not ask what your body is built from today, but where those building materials came from, how far they traveled and what they were doing along the way. You are made of hydrogen. About 62% of the atoms in your body are hydrogen atoms. Not by mass. Hydrogen is the lightest element, 1 proton and 1 electron, and by mass, the heavier elements dominate your body's composition. But by count of atoms, hydrogen is the most abundant, and as we have been describing throughout tonight, most of that hydrogen is primordial. It was made in the Big Bang nucleosynthesis. In the window between roughly 2 and 10 minutes after the Big Bang, when the universe had cooled to the point where deuterium could survive, but was still hot enough for nuclear reactions to proceed at a significant rate. The protons that are the nuclei of those hydrogen atoms were formed at around 1 microsecond after the Big Bang, when the quark-gluon plasma cooled below 2 trillion degrees, and quarks bound together into hadrons. Those protons survived the matter-antimatter annihilation that swept through the universe in the hadron epoch. They were the 1 in a billion excess, the asymmetry between matter and antimatter whose origin physics has not yet fully explained. They were present at the deuterium bottleneck, waiting while the universe cooled to 1 billion degrees. And when the bottleneck broke, most of them stayed as hydrogen, lone protons, the simplest nucleus, because there were not enough neutrons to incorporate them all into helium. Those protons have been protons ever since. They did not decay, they did not transform. The proton is, as far as we know, essentially stable. Its experimental lower bound on lifetime is around 10 to the 34 years, which is enormously longer than the current age of the universe. A proton formed at 1 microsecond after the Big Bang is, in all measurable properties, identical to a proton formed yesterday. It is the same particle, unchanged. The hydrogen proton in a water molecule in your cell right now is in every observable sense the same kind of particle that was formed in the quark-gluon plasma. Some specific hydrogen protons in your body have never been inside a star. They floated in the primordial gas for hundreds of millions of years. They became part of molecular clouds. They were incorporated into the solar system, into the ocean, into the biosphere, into food and water and air, and eventually into you, without ever passing through a stellar core, without ever being fused into a heavier element, just hydrogen, from beginning to now, 13.8 billion years of hydrogen. In your cells right now, you are made of oxygen. Oxygen is element number 8 on the periodic table. 8 protons, 8 neutrons in its most common isotope. It is the 3rd most abundant element in the universe by mass, after hydrogen and helium. In your body, oxygen makes up about 65% of your mass, more than any other element. The oxygen in the water that fills your cells, the oxygen bound to carbon in organic molecules, the oxygen that your hemoglobin carries through your blood. All of it was made in stars. Specifically, oxygen-16 is made in the carbon-burning stage of massive stellar evolution. When the carbon in a stellar core begins to fuse, carbon-12 combines with helium-4 to produce oxygen-16. This is one of the most important nuclear reactions in astrophysics. It is responsible for most of the oxygen in the universe. The rate at which this reaction occurs determines the ratio of carbon to oxygen produced in stellar cores, which has downstream consequences for the chemical evolution of the galaxy and the chemistry available for life. The oxygen in your body was made in stellar cores over billions of years, in stars that were born from the primordial hydrogen-helium gas that fused their way through the nuclear burning sequence that exploded in supernovae and scattered their oxygen into the interstellar medium. Multiple generations of stars across billions of years contributed to the oxygen that eventually became part of the solar system's material, and then part of the Earth, and then part of the ocean, and then part of the biology that eventually produced you. You are made of carbon. Carbon is, in a very real sense, the element of life. It can form 4 strong covalent bonds simultaneously, allowing it to build the long chains and rings and branching structures of organic chemistry. Proteins, the molecular machines of the cell; DNA, the information storage molecule; lipids, the fats that form cell membranes and store energy; carbohydrates, the sugars and starches of cellular metabolism. All of these are fundamentally carbon compounds. The extraordinary complexity of biochemistry is, at its root, the extraordinary versatility of carbon as a building material. Carbon is made in stars by the triple alpha process, 3 helium-4 nuclei alpha particles combine to form carbon-12. This reaction is notoriously improbable because the probability of 3 particles meeting simultaneously is very low. But it proceeds at a useful rate because of a specific nuclear resonance, a specific energy level in the carbon-12 nucleus called the Hoyle state. That allows the reaction to proceed through a 2-step process rather than requiring all 3 helium nuclei to meet simultaneously. This resonance was predicted by Fred Hoyle in 1953, before it was discovered experimentally. Hoyle's reasoning was simple. Carbon exists in abundance in the universe. Therefore, the nuclear physics must permit its efficient production in stars. Therefore, there must be a resonance in carbon-12 at roughly the right energy to allow the triple alpha process to proceed. He predicted the energy of the resonance. Experimentalists looked for it. They found it at very nearly the energy Hoyle had predicted. This is one of the most celebrated examples of what is sometimes called the anthropic argument in astrophysics. The fact that we exist and are made of carbon implies that carbon can be made efficiently in stars, which implies specific properties of nuclear physics. It does not prove anything about the universe being designed for our existence. The same properties that allow carbon production were set by the fundamental constants of nature, which we observe to have the values they have without any ability to vary them. But it illustrates how the existence of observers constrains the physics that must be possible. The carbon in your DNA was made in the helium-burning phase of stellar evolution. It was distributed into the interstellar medium by stellar winds and supernovae. It was incorporated into molecular clouds and then into stars and planets. It became part of the Earth's geological inventory and then part of the chemistry of early life. It has been passed through biological systems for billions of years, through the long chain of evolutionary descent that connects the first living cells to you. And it is now in the information molecules of your cells, encoding the instructions for everything your body does. You are made of nitrogen. Nitrogen makes up the backbone of amino acids, the building blocks of proteins. It is part of the nucleotide bases adenine, guanine, cytosine, thymine, uracil that encode information in DNA and RNA. It constitutes about 3.3% of your body's mass, and it is ubiquitous in the chemistry of life. The atmosphere is 78% nitrogen gas, and the nitrogen cycle, the process by which nitrogen moves between the atmosphere, the soil, and living organisms, is one of the most important biogeochemical cycles on Earth. Like carbon and oxygen, nitrogen was made in stars. In the carbon-nitrogen-oxygen cycle that powers many massive stars, nitrogen is produced as an intermediate product. Nitrogen-14, the most abundant isotope, is produced in stellar interiors and distributed through the interstellar medium. You are made of iron. Iron is element 26 protons in the nucleus, and in its most common isotopes, 28 to 32 neutrons. It is the most tightly bound nucleus in nature, the final product of fusion reactions in massive stellar cores, the wall that ends stellar nucleosynthesis. And it is in you. The iron in your hemoglobin. Hemoglobin is the protein in red blood cells that carries oxygen from the lungs to every tissue in the body. At the center of each hemoglobin molecule is a heme group, a flat, ring-shaped molecule with an iron atom at its center. That iron atom is the actual binding site for oxygen. Without it, hemoglobin cannot do its job. Without iron, your cells cannot receive oxygen. Without oxygen, they cannot produce energy. Without energy, nothing works. The iron at the center of your hemoglobin was made in the core of a massive star. It was the final product of that star's nuclear burning sequence, the end point of the silicon burning process, when silicon and its products were progressively fused into iron. When the star exhausted its energy source and its iron core collapsed, the explosion scattered that iron into space. Some of it, after billions of years of dispersal and recollection through the galaxy, ended up in the molecular cloud that became the solar system. It became part of the Earth. It became part of the chemistry of life. It became part of the hemoglobin in your blood. Right now, your heart is beating. Blood is moving through your body. Oxygen is being carried to your cells by proteins whose function depends on iron that was forged in the death of a star. Your life at this moment is running on stellar ash. This is not metaphor. This is chemistry. This is the literal, physical truth of where the iron in your blood comes from. Now, let me draw the thread all the way back. Every atom in your body traces back, ultimately, to the first 10 minutes of the universe. Not because every atom was made in those 10 minutes, the heavier elements were made later in stars, but because the protons and neutrons that make up every atom were made in the first microsecond, in the cooling quark-gluon plasma, and the light nuclei were made in the first 10 minutes by Big Bang nucleosynthesis. The protons in the oxygen nucleus in your blood, all 8 of them, were made in the quark-gluon plasma of the first microsecond. They were once free quarks, swimming in the plasma. They bound together at hadronization. They survived the matter-antimatter annihilation. They were present at nucleosynthesis, some of them incorporated into helium, the hydrogen ones remaining free. Later, those protons, or protons like them, interchangeable and identical, were incorporated into stars, fused together in stellar cores to make oxygen, scattered by supernovae, incorporated into the solar system and the Earth and the biosphere and you. The protons did not change in all of that. They were fused into different configurations, reorganized into different nuclei, incorporated into different atoms, but each proton remained a proton throughout. 2 up quarks and a down quark, bound by gluons, carrying its charge and its mass across 13.8 billion years of cosmic history. You are made of the first microsecond. Every atom, every nucleus, every proton and neutron, they date to the beginning, and the quarks inside those protons and neutrons, the up quarks and down quarks that are the most fundamental constituents of ordinary matter, those were present in the quark-gluon plasma. They were produced in the hot, dense, post-inflationary plasma. They came from the energy of reheating after inflation. And that energy came from the inflattened field, which descended from whatever conditions existed at the Planck time, which is the furthest back our physics can reliably go. You are made of the Planck era. You are as old as physics can currently describe. There is a thought experiment I want to offer you. Right now, the atoms in your body are at rest. Not completely at rest. Atoms are always moving. vibrating in their thermal motion, the electrons in quantum states around their nuclei, the quarks inside the protons moving rapidly in their tiny confinement. But at the scale of the body, the atoms are in the same place they were a moment ago. They are in the configuration that is you. And that configuration is extraordinarily improbable, not in a bad sense. In the sense that it required an extraordinary series of steps to arrive here. The specific arrangement of atoms that constitutes a living, thinking, feeling human being is a configuration of matter that the universe spent 13.8 billion years developing the conditions for. Not planning, the universe does not plan, but building up, step by step, the physical and chemical conditions that make such arrangements possible. The Big Bang provided the protons and neutrons. The cooling of the first seconds provided the ratio of protons to neutrons. The nucleosynthesis provided the hydrogen and helium. The Dark Ages provided the time for gravitational structure to develop. The first stars provided the carbon and oxygen and other elements. The subsequent stellar generations enriched the interstellar medium further. The solar system provided a planet with water and rock and the right temperature range for liquid water. The Earth's chemistry provided the conditions for the origin of life. Evolution across billions of years built complexity from those first living cells to you. And at each step, the laws of physics were operating as they always have. No step was magic. No step required anything beyond the ordinary working out of physics and chemistry and biology. Each step followed from the previous one according to natural laws. The extraordinary thing is not that any single step was miraculous. The extraordinary thing is the whole chain. The extraordinary thing is that it worked. That 13.8 billion years of natural law applied to a universe that began with almost nothing produced this. A configuration of matter that knows it exists. A universe that has become aware of itself in at least some small region. You are that region. This room tonight is a place where the universe is aware of itself, and the atoms that make up that awareness, the hydrogen and carbon and oxygen and iron and all the rest, they were made in the processes we have been describing tonight. In the quark-gluon plasma, in the nucleosynthesis, in the stellar cores, in the supernovae. They came from the beginning, and they are here now in you, carrying no memory of all they have been through, carrying no anticipation of all they will be after you are done with them. Just existing, in the present configuration in this room. Tonight, the hydrogen in your cells has been hydrogen for 13.8 billion years without needing to understand that fact. It just was. It just is. Moving through whatever forms it finds itself in, with no awareness of the quark-gluon plasma it came from, or the star systems it passed through, or the organisms it was part of before you, just a proton and an electron, in whatever arrangement the universe currently places them. You can rest as easily as the hydrogen rests. You are what the Big Bang became when it had 13.8 billion years to work with. Every configuration of matter the universe has passed through, every star that burned, every supernova that scattered elements across the galaxy, every molecular cloud that collapsed, every cell that divided, all of it was part of the process that produced you. Not for the purpose of producing you. There was no purpose, but you are, nonetheless, the result. The universe made something that wonders about the universe. From quarks and gluons and a 1 in a billion asymmetry and 13.8 billion years of patient physics, it made this. A mind lying in the dark, thinking about where it came from, which is, if you let it be, the most remarkable thing imaginable. Let me try to bring this all the way down to the scale of a single breath. Right now, you are breathing. Air is moving into your lungs, oxygen crossing from the air sacs into your bloodstream, carbon dioxide crossing back out, the spent gas of cellular metabolism returning to the atmosphere. This is happening automatically, without your direction, as it has been happening your entire life. In each breath, You take in roughly half a litre of air. That air contains about 10 to the 22 molecules of nitrogen and oxygen and trace gases, a 10 with 22 zeros after it. More molecules than there are stars in the observable universe. Each molecule of oxygen, O2, contains 2 oxygen atoms, each with 8 protons and 8 neutrons in the nucleus. Those protons and neutrons were assembled, as we have described, in the stellar cores of massive stars billions of years before the solar system formed. The oxygen atoms were distributed into the interstellar medium by supernovae. They became part of the Earth's early atmosphere over geological timescales. They have been cycling through the biosphere for billions of years, in and out of living organisms, in and out of rocks and ocean and atmosphere, in and out of countless billions of living things since the origin of photosynthesis around 2.7 billion years ago. And now, in this breath, they are moving through you. Each oxygen molecule you breathe in will spend less than a second in your lungs before crossing into your blood. It will travel in the red blood cells carrying it, through your heart and out to your tissues. In your tissues, it will diffuse into cells and into the mitochondria, the small organelles that are the powerhouses of the cell, the descendants of ancient bacteria that merged with early eukaryotic cells 2 billion years ago. In the mitochondria, the oxygen will be used to power the cellular reactions that produce ATP, the energy currency of the cell, and the carbon dioxide produced by those reactions will travel back through the blood to the lungs and out in your exhaled breath. The whole cycle takes on the order of a minute. In that minute, oxygen atoms that were forged in stellar cores billions of years ago, that crossed the big galaxy in the blast wave of a supernova, that drifted in molecular clouds, that became part of the Earth's atmosphere, that have been cycling through the biosphere since before complex life existed. Those atoms are, for 1 minute, powering your cells. Then they leave. They go back into the atmosphere as carbon dioxide now, carbon from your biology, oxygen from the stellar cores, back into the carbon cycle, back into the biosphere, back into the world, and you breathe in again. More ancient oxygen, more stellar core nuclei, more ancient matter, cycling through you, powering you for another minute, and then moving on. This is happening right now. This is your life, in physical terms. Ancient matter flowing through a temporary structure, your body picking up energy along the way and flowing out again. You are not a fixed collection of atoms. You are a pattern through which matter flows. The atoms that constitute you today are different from the atoms that constituted you 7 years ago. Cells die and are replaced. Molecules are metabolized and expelled and replaced. Your body is a process, not a thing, a river, not a rock, but the pattern persists. The arrangement, the specific, intricate organization of matter that is you, that processes information and has experiences and wonders about the universe. That pattern continues, sustained by the flow of ancient matter through it. You are a pattern in the universe's matter, a pattern that the universe has been building up the conditions for 13.8 billion years, a pattern that can wonder about itself. And tonight, for a few hours, the flow slows, the metabolism quietes, the pattern rests. The ancient atoms in your cells do their overnight work, the quiet, patient work of maintenance and repair, while the awareness that the pattern produces drifts into sleep. The oxygen from the stellar cores keeps flowing through. The hydrogen from the Big Bang is still in your cells, still bonded in its water molecules and organic compounds, still part of you. The iron from the supernovae is still in your blood, still carrying oxygen to your brain, still keeping the neural tissue alive that produces the awareness that can hear this story. Everything is still working. Everything is still there. The universe, in this small patch of it, is quietly sustaining itself while it rests, and that is enough. More than enough. The universe is 13.8 billion years old tonight. That number does not fit comfortably in the human mind, and I do not think it is supposed to. The mind is built for a different scale, for the scale of a life, a landscape, a community, a history that can be told in days or years or centuries. The 13.8 billion years of cosmic history is simply too large for direct intuitive grasp, and that is all right. You do not need to hold it in your imagination to feel what we have been describing tonight. You just need to feel the weight of your body. You just need to notice the room you are in. You are lying somewhere. A bed, a floor, a couch, somewhere that is holding your weight, that has been holding your weight for however long you have been lying there. The surface is made of matter. Wood or metal or foam or fabric or stone, whatever it is made of atoms. And those atoms have a history that runs, without interruption, from the first microsecond of the universe to this moment, to right here, to the surface beneath you. The wood, if there is wood, made of carbon and oxygen and hydrogen, carbon forged in stellar cores, oxygen forged in stellar cores, hydrogen from the Big Bang and nucleosynthesis. The cellulose in the wood organized those atoms into long polymer chains by the chemistry of a living tree, which got its carbon from the atmosphere and its hydrogen from water and its oxygen from both. The tree's carbon came from CO2 in the air, and that carbon was once part of animals and plants and microbes and geological processes stretching back billions of years. Before it was in the atmosphere, it was in the ocean. Before it was in the ocean, it was in volcanic emissions. Before it was in volcanic emissions, it was in the mantle of the Earth. Before it was in the mantle, it was in the solar nebula. Before it was in the solar nebula, it was in the interstellar medium, ejected by some stellar explosion billions of years ago. The chain does not break. The atoms in the surface that is holding you right now are the direct descendants of matter that was present in the early universe. Some of the hydrogen in that wood or that fabric, the hydrogen bonded to the organic molecules, the hydrogen in the water absorbed into the material, is primordial. It was made in the first 10 minutes. And the air in this room, the nitrogen and oxygen molecules moving in and out of your lungs with every breath you take. Every slow, quiet breath as you listen and your eyes grow heavy. Those molecules are made of atoms that came from stars. The nitrogen was made in stellar interiors. The oxygen in carbon-burning shells of massive stars, both distributed into the galaxy by supernova across billions of years. Both incorporated into the molecular cloud that became the solar system, both cycling through the Earth's atmosphere and biosphere and geology, and eventually into the air in this room, right now, moving through you. You are breathing the remnants of dead stars, literally. Every breath and your body, your particular body, the specific configuration of matter that is you tonight in this room. The hydrogen in your cells, 62% of your atoms by count, the most abundant element in you, is mostly primordial, made in the first 10 minutes, never inside a star. As old as the universe itself, some of it having been hydrogen since the nucleosynthesis era and remaining hydrogen through every subsequent chapter of cosmic and geological and biological history. Those specific protons have been part of the ocean and the atmosphere and the geology of the Earth and the food chains and the water cycles, and eventually you, but they have been protons, identifiable as hydrogen nuclei, for 13.8 billion years. The oxygen in your cells, made in stars, distributed by supernovae, incorporated into the Earth and the ocean and the chemistry of life, is in your water, in your proteins, in your DNA, in the hemoglobin carrying oxygen from your lungs to your brain right now, in every organic molecule, in every cell in your body. The carbon in your DNA, made in the triple alpha process in stellar helium burn zones, scattered across the galaxy, incorporated into the solar system and the Earth's surface and the biosphere, is the basis of every information carrying molecule in your cells, the backbone of every protein, the ring structure at the center of every base pair in the double helix that encodes you, the iron in your blood, forged in the silicon burning process at the core of a massive star, scattered in the supernova that ended that star's life, drifting in the interstellar medium, incorporated into the solar nebula, becoming part of the Earth, cycling through geological and biological processes, finding its way into hemoglobin, is right now carrying oxygen to your brain, keeping you alive, keeping the neurons firing. You are made of 13.8 billion years of cosmic history, every atom, without exception. And right now, all of those atoms are at rest, in the quiet, in this room, in you. There is a particular quality to this thought, the thought of what you are made of, where those materials came from, what they have been through, that is different from other calming thoughts. It is not a thought about relaxing the body or quieting the mind in some mechanical sense. It is a thought about context, about scale, about your place in a story that is unimaginably larger than any individual life, but that your individual life is genuinely and irreducibly a part of. The universe began. It has been developing ever since, becoming more complex, more differentiated, more structured, more interesting with every passing era, from the uniform hot plasma of the first second to the quark gluon plasma, to the nucleosynthesis, to the dark ages, to the first stars, to the complex multi-element chemistry of later stellar generations, to the solar system, to the Earth, to the biosphere, to you. You are not an observer of this process from outside. You are the process. You are the universe at a particular stage of its development, the stage where it has developed the capacity to be curious, the capacity to ask questions, the capacity to lie in the dark and wonder about the beginning. That is not a trivial stage. It required 13.8 billion years to reach. There is something that the physicist and author Alan Lightman wrote once, in a context different from this, but applicable here. He said that human beings are, as far as we know, the universe's only means of contemplating itself. We may be wrong about that. There may be other minds elsewhere in the vastness of the cosmos. We do not know. But we know that we are one place where the universe has become aware of itself, where the matter that emerged from the Big Bang has organized itself into something capable of wondering about the Big Bang. That is extraordinary, and it is you. The atoms in your brain right now, the carbon and oxygen and hydrogen and nitrogen and phosphorus and sulfur and all the rest, are doing something that has never been fully explained by any science. They are aware. They are experiencing. There is something that it is like to be you, lying here, listening to this. There is an inside to the experience, and we do not know how or why the specific arrangement of atoms that constitutes a brain produces the fact of awareness. This is, in a sense, the deepest mystery still open in science. Deeper, in some ways, than the mystery of baryogenesis. Deeper than the details of inflation. We can describe the physics of the early universe with remarkable precision. We cannot explain why there is something that it is like to be the arrangement of matter, called a person. But it is here. Whatever it is here. In you, right now, in this room. In these atoms that came from the Big Bang and the quark-gluon plasma and the nucleosynthesis and the stellar cores and the supernovae and the long drift of the interstellar medium and the formation of the solar system and the cooling of the Earth and the origin of life and the 4 billion years of evolution that preceded you. All of that history organized into awareness, lying still in the dark for just a few hours. Let me tell you what happens to the atoms in your body while you sleep. The biochemistry does not stop. Your cells continue their work, repairing DNA, producing proteins, clearing cellular debris, consolidating memories in the neural circuits of your brain. Your heart continues to beat. Your lungs continue to move air. Your neurons continue to fire in the slow rolling rhythms of sleep. Life does not pause for rest. It just changes modes. But at the scale of atoms, at the level of the protons and neutrons and electrons that constitute everything, there is something that the words rest and quiet genuinely apply to. The thermal motion of atoms in a solid is less than in a liquid, less than in a gas. Your body at rest in a warm room is not in any thermodynamic extreme. The atoms are simply doing what atoms do, vibrating in their chemical bonds, moving through their quantum states, participating in the biochemistry of a living organism. What they are not doing is anything dramatic. They are not being fused in a stellar core. They are not being scattered in a supernova. They are not drifting through interstellar space. For these few hours, they are in one place, in one body, in one room, doing the quiet chemistry of sleep. This is in the context of their 13.8 billion year history, a very quiet period. They have been hotter. They have been in stellar cores at millions of degrees. They have been in the plasma of the early universe at billions of degrees. They have been in the quark-gluon plasma at trillions of degrees. Right now they are at 37 degrees Celsius. The most extreme temperatures in the history of atoms, billions of degrees in the quark-gluon plasma, millions of degrees in stellar cores. And right now they are in a body at 37 degrees. In a room somewhat cooler, in the quiet of a night that will end with morning. There is something settling in that, not in a small sense, in a genuinely settling sense. The atoms have been through more than we can easily imagine, and they have arrived here, at this temperature, in this configuration, in this room. The universe began in fire and extraordinary violence and temperatures beyond imagination. It has been cooling and expanding and organizing and developing for 13.8 billion years. And here, at this particular point in that process, there is a room where the products of all that development are lying still and quiet, at a comfortable temperature, in the dark. That is what the universe has produced. You, here, tonight, the beginning happened. The quark-gluon plasma happened. The nucleosynthesis happened. The dark ages happened. The first stars happened. The stellar generations happened. The solar system happened. The Earth happened. Life happened. Evolution happened. You happened. And all of it led to this, to a room, to a body, to a few hours of rest. There is a physicist's phrase I want to use carefully here, because it is often used carelessly. The phrase is, "We are made of stardust." You will have heard it. Carl Sagan said it, among many others. It is true in a specific and meaningful way. The heavy elements in your body were made in stellar interiors and scattered by stellar explosions. You are in that sense stardust. But you are more than stardust. The hydrogen in your cells was not made in a star. It was made before any star existed, before any star had formed. In the first 10 minutes of the universe, when there were no stars, when there were no galaxies, when there was just the hot, expanding plasma of the early cosmos. You are also Big Bang dust. You are nucleosynthesis. You are the residue of the matter-antimatter annihilation, the 1 in a billion surplus that did not annihilate, that survived, that eventually became everything. You are the product of cosmic inflation. Your particular galaxy seeded by a quantum fluctuation, that inflation stretched to cosmic scales. You are the cooling of the universe. Every degree of temperature drop from 10 to the 32, down to the 37 degrees in your cells is part of the story of how you got here. You are the dark ages, patiently waiting for gravity to work. You are the first stars and their deaths and the elements they scattered. You are the interstellar medium and the molecular cloud and the solar nebula and the cooling Earth and the first cell and 4 billion years of evolution. You are all of it. Every chapter, every era, every stage of the universe's 13.8 billion year development contributed something to the configuration of atoms that is you tonight in this room. And for just a few hours, that configuration is at rest. The universe made something capable of rest. That is, if you think about it, one of the universe's more quiet achievements. After all the fire and the pressure and the nucleosynthesis and the stellar death and the long, slow development, it made something that can stop for a while and be still. You can stop for a while and be still. The hydrogen in your cells will still be hydrogen when you wake. The iron in your blood will still be iron. The carbon in your DNA will still hold the instructions for everything your cells need to do. The protons at the nuclei of every atom in your body will still be the protons they have been for 13.8 billion years. Nothing important will have changed while you slept. The universe will have expanded a tiny bit further. The cosmic microwave background will be a tiny bit colder, by an amount so small it could not be measured. The distant galaxies will be a tiny bit further away, but this room and your body in it will be essentially as they are now, resting in the dark, in the quiet. The atoms at a temperature comfortable for life. The mind drifting towards sleep, the long journey of matter pausing for a few hours. You are what the universe became when it had enough time. And tonight, for a few hours, you can rest in that. The beginning happened. You happened, and that is enough. Good night.